Hi everyone and welcome back to PrepFusion. So few students were asking that they were feeling bit weak on the DC part, so they wanted some videos, some conceptual videos on the DC part. So I have tried to take all the Git PYQs from 2020 to 2025 of from these three chapters. Okay, the DC part uh, for BM, IN, EE, so EC and EE, right? This is the sequence in which we solve the questions, and you will feel that everything is easy, sir. I'll solve everything, but trust me, like everything is not easy. Like I will highly suggest you to watch this video, at least these three parts, right? In basics of network, I discussed this particular circuit, and many students have a doubt, like if I add a ground here, if I add a ground here, what will be the current? If I don't add a ground, what will be the current, right? So there is huge doubt here, right? So I have tried to explain this concept in a very lucid manner, right? In a crystal clear manner. So like at least watch this part from basis of network, at least watch this question, very important. Other questions are also important, right? You will see how I have explained, and it will be a good revision for you guys, right? And from transient, I will suggest watch the whole transient part, because most of the questions are very good from transient that has been asked, especially from EE. At least watch all the questions from EE, right? They were very good. From EC as well, good questions were asked. This is one of the questions that came recently, previous year only, and this is a very good question actually. You can solve it in seconds, but to solve this in seconds, you will need fundamental knowledge, lot of knowledge. Okay, so yeah, then you can solve it. So I have taught this, but before watching this solution, first you watch this solution, right? This from W only. Again, very good question. Here I have tried to explain most of the things in pulse response. I will not be able to explain everything, but most of the things I will try to explain here. First watch this, then you can watch this particular part if you are planning to skip it, but I will suggest watch the whole transient response. That will be a very good revision, because transient, they have asked good questions from transient, so don't skip it, right? The basics, you can watch this part. Theorems is mostly easy, you will be able to solve it. If you are feeling confident, no need to watch that, but at least watch this part, very important. These three questions were very important. Now if you after watching this video, first you watch this video. Now if you need more practice, so there are good collections of questions, 80 questions on this video, right? R-PYQ network analysis. So you can watch this one shot in 80. There are, I don't remember exactly how many questions, not 80 actually. I don't remember how many questions, but there are a lot of questions that you can practice from here, and these are a level higher than Git. So this will be a bit difficult. So first you watch this video only, then you go and watch this video, right? And this video is there if you are feeling weak in AC part. So just watch this single video and you will be good to go. I'm talking about EC aspirants. If you're EC and you are feeling a bit weak, just watch this video, especially the resonance and the complex power and the two port as well. Two port is also covered here. So you can watch this one single marathon one shot, and you will be able to cover most of the syllabus of the AC part of network theory, right? Now I'm doing this much. I have I have not slept for previous night, so I was trying to get this video to you guys as early as possible, so I did not sleep. So I'm expecting a bit of things, otherwise I will just keep it only for the PH students, this video. So I'm like you watch the video, you guys just can watch these three questions and you will realize what is the quality of content. So if you want this video to remain on YouTube, just a bit of request from my end is like the video, right, and comment down below whatever you feel. You can watch these questions and you will certainly realize like what is the level of the content. I know, because I have seen the other contents, right, everywhere else, so I know the level of content. So you can watch these three solutions and you will realize. So comment down below whatever you feel regarding this video. Then if I receive enough views and comments in this video, then I will keep it, otherwise I will only keep it for the paid students. So it's up to you what you do. So yeah, let's begin with the first chapter, that is basics of networks. So let's begin with the first chapter, that is basics of networks. So first we'll solve IN questions, then BM, then ECE, and then EE. So initially the questions will be on the easier side, and slowly the level of the questions will be higher, because EC and EE, generally the questions come out to be a bit difficult. So this is the first question. In the circuit shown below, the safe maximum value of current I is what? They're asking me what is the safe value of the current I. Do understand what do you mean by safe? Safe basically means the resistors should not be damaged. And when does a resistor gets damaged? when there is overheating. So if you see, in all the resistors, they have provided with some wattage rating and the resistance value as well. So I know that resistors follow this rule, very simple rule, I square R equals to the power rating of the resistor. So with this, I will be able to calculate the maximum current that each resistor can support without getting overheated or damaged. So let me compute for each of them. Let me compute for the first resistor. So I1 square into R. R is how much for the first resistor? It is 100 equals to 1. So I1 is actually equals to 1 by 10 amperes. That is the current of the first resistor. What about the second? So I2 square into R. R is given as 2. So into 2, what is the wattage rating? It is 0.5, that is 1 by 2. So your I2 comes out to be 1 by 2 amperes. And I3 square into R. R is 1 ohm and the rating is given as 0.25, that is nothing but 1 by 4. So your I3 is equals to 1 by 2 ampere. So out of this, right, what you will say is your safe limit for the whole circuit, because everything is in series, right? If you say that I will choose half as my safe limit, where half is also present in the option, then what will be the problem? The problem would be these two resistors will be safe. But if half amperes flows through the first resistor, the wattage will be how much? It will be 1 by 4 of 100, that is 25 watts. And my resistor can only support 1 watt, right? It cannot burn 25 watts. So certainly this will be large. So whenever everything is in series, if you have to choose the highest current that all the resistors will support, you will have to choose the minimum of the three, right? Then only all three resistors will support them without any problems. That is 1 by 10 in this case, that is 0.1 amperes. So 0.1 will be the answer for this particular question. So yeah, let's move to the next one. Now this one is again pretty interesting, pretty basic question, but seems very lengthy at first glance. So they are telling me that I1, I2, I3 are in the figure below are maze currents. The correct set of maze equations for these currents in the matrix form is. Basically they are asking me what are the matrix format of the maze equations. It's very simple, right? This question seems very confusing at first, but it's very simple. All you have to do is write the maze equations. That's it. One more thing I observed, that three options has the first row same, this one different, right? Other now second row, if I check for the second row as well, three options has the this same and this one is different. And the again the three options, like all four options, right? Okay, no, this is different, right? This is -3, this is +3, this is +3, +3, plus -3. So like you will not be able to eliminate the options that easily over here. All you need to do is write down two equations, right? And you're done. You can choose any two. Let's choose this loop and this loop, right? So let's first solve for this loop. So I hope you know how to write the maze equations. How do I write the maze equations? So I know you have already learned in basics. If you have not, simply I will tell you how to write the maze equations. So you will start from a point, this point A, and you will come back to the same point again, right? That's what maze means. Maze means you will come back to the loop. So we are simply applying the KVL, that's all. Now once I start from this point, what is the first sign that I observe? Negative. So that is the convention that I follow, right? Whatever I will write is my convention. Now if you have studied from somewhere else, they might follow some other convention. Okay, so please whatever I'm saying right now, like if you are comfortable with that, good. But if you already follow some other convention, follow your convention, right? All good. So I will start from this point, and if I start from this point, I will always go in the clockwise direction, and first I observe a negative sign. So I will write minus V1 because the potential here was V1, right? Because I observe a negative sign, so I will write minus. Then I will move and I will encounter this 1 ohm resistor. So there is a drop across this 1 ohm resistor. I see that this I2 current is flowing in this direction, correct? And the I1 current is flowing in this direction. So because I always choose my KVL along the direction of the main loop current, because this is the loop 1 and I1 is in the clockwise. So I1 is dominating. So what you will write? I1, simply what is happening? What is the current through this resistor? It is nothing but I1 minus I2, like not exactly I1 minus I2. Actually the current through the resistor is not I1 minus I2. All I am saying is the loop current, right? So I hope you have learned this in mesh analysis. So I1 minus I2, right? That is a loop current. So that is in this direction. So what is the drop? Current always enters in the positive terminals. So this is the drop. So let me write here 1, the resistance value, into I1 minus I2. Now the same thing we will repeat for this particular resistor. Again, in which direction I am rotating? Clockwise. So I am rotating along the I1 direction. So I1 is my master current and I2, if you see, is upwards. I1 is downwards, right? I am going along I1. So it will be I1 plus I1 minus I3, because I3 is against my direction of rotation, into the resistance value, that is the drop of this resistor, that is 2 ohms. That's it, right? So this will be equals to 0. So yeah, if I rewrite this equation, V1 would be equals to 3I1 minus I2 minus 2I3. Okay. Yeah, 2 into this, 3I1. Yeah. So 3 minus 1 minus 2. So the first row, right? So essentially we're making a matrix. So here I will have the this matrix multiplied by the I matrix, right? I1, I2, I3, I1, I2, I3, and here I will have the voltage matrix. This is nothing but the KVL equation. V equals to I into Z, or Z into I, right? So that is what is happening over here, if you see. So the first row should be what? 3 into I1 minus 1 into I2 minus 2 into I3. So 3 minus 1 minus 2, 3 minus 1 minus 2, 3 minus 1 minus 2. This is not correct. This also is not correct. So option A and B are my possible answers. Now let's do it for the second KVL. So if I write the KVL here, again I will start from somewhere here. So if I start from here, this will be the negative sign. Again, I am saying you again that if you follow some other notation, go ahead with that. I am just telling you, I am just telling for those students who are completely new here, who don't have any idea. So minus V2 plus I2, because remember here there is no current, right? Only I2 current is flowing. So I2 into 1. Again, I'm going in this direction. I2 is in the correct direction, but I3 is in the opposite direction. So plus I2 minus I3. I2 minus I3. And in this particular resistor, it is I2 minus I1 plus I2 minus I1 equals to 0. So again my V2 is equals to what? V2 is equals to 3I2. Okay, I will write the I1 first. Equals to minus of I1 plus 3I2 minus I3. Correct? So minus 1 plus 3 and minus 1. So minus 1 plus 3 and minus 1. Actually, we should not have actually solved the second KVL, because we see that for both of these options it is the same, right? Actually, we should have solved the third KVL. My bad. Okay. So that's what you will have to avoid in the exam hall. Here we have a lot of time. In the actual examination, you will not have much time. So you will see that both these particular rows are same. So I don't need to actually apply KVL in the second loop. I will directly jump to the third loop. So that's it. That should be a good observation. So yeah, let's actually solve the third loop. So this I will solve a bit quickly. Minus V3, sorry, Now I am going in this direction, right? And I see that plus sign is coming first. So I will write plus V3. Then this will be I3 minus, remember I3 is going here, I1 is going in the downward direction. So I3 minus I1 into 2 plus I3 minus I2 into 1. This is equals to 0. So your V3 would be equals to 2I1 minus, sorry, this will be plus I2 minus 2I3, correct? So 2, okay, something I have done a bit wrong. V3 is here, this will be I3 minus, I'm going in this direction, so I3 minus I2, I3 minus I2. So this will actually go in that direction, this will be plus only. Okay, I3 minus I1, so minus, sorry, this will be 2 and 3, right? Minus 3 and, okay, somewhere there is a discrepancy of the sign, so I'm coming from here, so I will choose this first, plus V3 plus I3 minus I1 into 2 plus I3 minus I2 into 1. This will be negative on that side. It seems like there is some discrepancy. I will have to check the question. For me, the V3 is coming out to be this. Okay, let me know in the comments below, like where I'm making the mistake, but I'm not able to see any mistake from my end. So this should be 2, 1 and minus 3. I don't see this option. So I am not able to figure out like exactly where I'm making the mistake. It seems like the options are not matching for me. According to me, it should be MTA, but I don't know. Maybe like you guys can let me know in the comments below wherever there is some discrepancy in the calculations. So yeah, we can definitely see that. So I don't know, like for, I think it should be MTA or somewhere I'm making a very silly error in the calculation mistake. It should not happen like this. So let's solve this one. Three resistive loads are connected to ideal voltage and current sources as shown in the circuit below. Okay, so three resistive loads are connected. All they are asking me the voltage VAB across the terminals A and B. So in this case, they are simply asking you the potential difference. So although you don't need a reference to compute the potential difference, for us we will make a reference, right? This point seems to be the best point to make a reference. If I make a reference, what will be VAB? VAB will be nothing but VA potential, sorry, VAB would be VA minus VB. VAB would be VA minus VB, right? Now, how do I calculate VB? So VB is very simple, right? From the ground, with respect to ground, what is the potential at point B? It is plus 24, right? It is plus 24. With respect to ground, it is plus 24. So VB is pretty simple, plus 24. How? Simply if I look at this point, right? So there is a potential difference between this point and the ground. That is what VB is. VB is basically the potential at this node with respect to the ground. That is what the node voltage VB means actually. What is it? It is nothing but this potential, right? 24 with respect to ground. What is the potential here? It is 24 volts, because at this node the potential is 0. At this node the potential would be plus 24. That's why VB would be plus 24. Now what about VE? For VA we can simply apply nodal. VA by 10 plus VA. I know already what is the potential here, that is 24, right? So VA minus 24. So I hope you already know what is the how to apply the nodal. So in my case, again, I assume a reference. What is the reference? That I assume that if I am taking a nodal at this particular point, right, I will assume all the currents are outgoing except a current source. I cannot control the current through a current source, so it is incoming, that is fine. So all my outgoing currents will be positive and all my incoming currents will be negative. So what is the potential here? VA minus, what is the potential here? 0 divided by 10. So VA minus 0 divided by 10. That's how this came, VA by 10. Right? Potential difference by the resistance value would give me the current, plus VA minus VB, and I know what is VB, plus 24. VA minus VB, that is 24, divided by the resistance. These two are in series, right? That's why I am able to do this kind of simplification. So this divide by 50 plus, now I told you, right, these two are the branches for this current is outgoing. I cannot control the current here, it is incoming. So I will write here plus minus of 1.2 because this is a incoming current. So these are all the currents, right? And according to KCL, we know sum of all the currents at a particular node will always be 0. So this will be 0. So this will be 5, so 6 VA by 50 plus, so yeah, this will go on that side. This will be 2.4 by 5, 2.4 by 5, so 5 multiplied by that, 6 by 5, so it will be 8.4 divided by 5. So this kind of calculations you should be able to do mentally without going into the calculator. So this will be 10, 10 will go there. This will be VA 84 divided by 6, which is nothing but 19 volts. So not 19, sorry, 14 volts, right? Because 6 into 15 is 90. So VA is 14 and VB is 24. So VAB would be 14 minus 24, that is minus 10 volts. So minus 10 volts would be your answer for the question. Let's solve this question. Power consumed by the 3 ohm resistor is 12 watt in the given circuit. So in the 3 ohm resistor, the power consumed is 12 watt. The value of R in the circuit is what? So if in the 3 ohm resistor, the power consumed is 12 watt, what will be the current through the resistor? We can use this simple formula, I square into R equals to power consumed, right? So I would be equals to 12 divided by 3 whole under root. So I would be equals to 2 amperes, right? It will be plus minus 2. So I can be either in this direction or in this direction. Now which direction shall you choose? For a resistor, it is very simple. Whatever it will be the plus terminal, the current will be incoming because a resistive load can only absorb power, it can never deliver power. So there is no confusion. Now what do I see here is I see the potential plus minus like this, right? And all these are resistive loads. So the potential will be divided somewhat like this, right? V1, V2. It will be plus minus like this only, right? Because all these are absorbing kind of loads. So all these will absorb the power, right? They cannot deliver. So if it is plus minus like this, so certainly I know this will be the proper direction of the current. This will not be the direction of the current because current can only enter the positive terminal for a resistive load. So we got the current, we got the current direction. What is the voltage? What is this V2? V2 is actually very simple, right? All these are in parallel. So this is 2 into 3, that is 6 volts. So if V2 is 6 volts, V1 is also very easy to calculate. It is 4 volts because your overall 10 volt would be equals to V1 plus V2. Very simple, very straightforward, not very difficult, right? So V1 plus V2. Great. Now what you need to do is you got V1 and V2. You got this current 2 amperes. Now what will be the current here? I don't know. I don't know what is the current here, right? Because this particular value I don't know. Okay, that is fine. So we can use bit of smartness. Like there are multiple ways to solve this question. You can find out the equivalent resistance, you can find out the current, and then from that you can do this, right? There are millions of ways to solve this question. But what we know is the ratio of the voltage across this resistor and ratio of the voltage across this resistor will be proportional to their resistance. Why? Because we know voltage is equals to current into the resistance, right? And I know, let's name this particular resistor as R1 equivalent, right? And let's name this as R2 equivalent. So basically in R1 and R2 the currents are the same, right? If currents are the same, their V1 upon V2 will be, currents are same, right? So it will be simply R1 upon R2. I already know what is V1, 4. So it is 4 upon V2 is 6, R1. Now how do I calculate R1? It is the R equivalent, 2 into 1 upon 3, that is 2 by 3. What is R2? R2 would be 3 into 2 upon, let me write this R2 for now. Let me keep it R2, right? Then I will solve it. Let me keep it R2 for now. So this is also 2 by 3 only, right? This will cancel out to 2 by 3. So your R2 equivalent actually comes out to be 1 ohm. So all this equivalent will come out to be 1 ohm. Very convenient, right? So basically 1 by R2, right, equivalent will be equals to, all these are in parallel, so 1 by 3 plus 1 by 2 plus 1 by R. Very basic equation of equivalent resistance in parallel. So what will happen here? So 1 by R, this would be 5 by 6, that will be 1 by 6 basically. So your R would be equals to 6 ohms. So this will be your answer for the question. Pretty simple and pretty straightforward. There are a lot of ways to solve this question, but how can you solve it using the most efficiency and fastest? Like that is the important point. This question is pretty simple, but you will have to solve this simple question in a faster manner so that you can give more time on the difficult questions. That's the point of this video, right? To tell you that how to solve it in a most efficient manner. The magnitude of the current gain I load upon I in the circuit below is what? So simply they are asking me the magnitude of the current gain. How do I compute magnitude of the current gain I load upon I in? So let me define my parameters. I know there is a ground here and which might cause a lot of confusions, and don't worry, there will be a question just few like just in a bit where we will discuss about this ground. For now the discussion is not this ground, the discussion is pretty simple. Are these two resistors in parallel? Yes. Whatever is the potential between these 2 points, I have the same potential, right? Basically, if this is point A, this point B, both these AB points are common for both the resistors. So both of them are in parallel. If both of them are in parallel, then their currents also will be in opposite ratio. How? If voltage is same, right? Voltage is same. Voltage is equals to what? I into R. So I1 into R1 would be equals to I2 into R1, R2, because the voltage is same. So I1 upon I2 would be equals to R2 upon R1. That's very simple, right? What is I1? So let me assume this to be my I1 current, this to be my I2 current. So I1 is IB, I have to compute I2. R2 is what? R2 is 5 kilo ohms. Everything is in kilo, so I am very safe. Everything is in the same units, so I don't have to write kilo in 10 raised to power 3, because as everything is in kilo, I don't worry about it. So 5 kilo upon 1 kilo. So your I2 would come out to be IB by 5. So this is your IB by 5. This will help us out a lot. How? I know if I apply a KCL at this node, I in would be equals to IB plus IB by 5. So I in is equals to IB, incoming current will be equals to the outgoing currents, IB by 5. So your IB actually is equals to 5 by 6 of I in. This will help out here. That's why I had to do all this mathematical manipulations. So what will be your now let's apply the same principle here. Again, these two resistors are in parallel. So if this current is I load, right, IL, then the current I2 in the other branch, I2 dash, would be equals to what? Ratio of their opposite resistance. Current in that particular branch is ratio to the opposite resistance. So this branch will be 10, right, because I will choose the opposite upon 1. So this is very basic current division rule which I know you have studied, correct? So 10 by 1. So your IL, so I2 dash, right, would be equals to IL by 10. So current, now remember the direction should be same, right? Both of them are resistive loads. So plus minus, right? So current direction should be same. Both of them are resistive. Here also plus minus. So here also current direction should be inside the positive terminal. So this current is IL by 10. So again, if I apply a KCL at this particular node, now things are pretty interesting here. All the currents are outgoing. And what have I told you? I will follow my convention. What is my convention? Outgoing currents are always positive. So this will be 100 IB plus IL by 10 plus IL equals to 0. So now what is IB? IB is pretty simple. IB is 5 by 6 of I in. So this will be and this will be minus 11 by 10 into IL. So your IL, what have they asked? They have asked us I load. IL is my I load basically. IL by I in would be equals to 50 into 10, that is 500 upon 33 minus 500 upon 33. Am I correct? Hold on a second. 5 into this. Sorry, 15 to 5, right? So 15 to 5 would be 2500. 15 to 50, 15 to 50 basically. 15 to 50 would be 2500 upon 33. Now what have they asked? They have asked, remember, they have asked the magnitude. So they have made it pretty clear. They want the magnitude of the current gain. They don't want the actual value. So if they want the magnitude, IL by I in, this will be 2500 upon 33. That is, if I calculate this value, this will be what? 2500 upon 33, 75.75. So yeah, this will be your answer. 75.676. This will be your answer for the question. They have asked us to round off to 2 decimal places. So this is the answer. Right? Pretty straightforward, but you will have to be good at with the numbers and also with the directions. Remember, current always enters into the positive terminal for a resistive load. So here, if already they have given you the direction of current, that means this will be plus, and if this is plus, here also the current will be entering in this particular terminal only, positive terminal only. Here also the same thing. And you know, if you have studied current division, you know that if the two resistors are connected in parallel, the current ratio would be in opposite to their resistance, right? So current here would be this, and current here in this resistor will be according to this. So this is higher, so that's why IL is higher, and this current is IL by 10. I hope you got the intuition. let's solve this question. Pretty simple again. The circuit below is shown. The two DC voltage sources have voltages V1, V2. The expression for power dissipated in the 60 kilo ohm resistor is proportional to what? Right. So the power dissipated in the 60 kilo ohm resistor is proportional to what? So basically, what is the power dissipated across the 60 kilo ohm resistor? It will be V square by R, right? So it is basically proportional to V square because voltage is the factor, R is a constant number. So what is the voltage? How do I compute the voltage? So for computing the voltage, again you can apply simple nodal. You assume a node potential here V. If I assume a node potential here V, this will be V minus 0 160. Now remember everything is in kilo, so you don't have to worry. What do I need to write? Do I need to write 60 into 10 cube or only 60? If everything is in kilo, don't worry. Write in 60. The moment you write here in 60 kilo, right, that basically means this current, because V is in volts, this current will be in milliamperes. So this thing only you will have to keep in your mind while only writing 60. You know it is 60 kilo. If you're writing 60, that means the current, right, is in milliamperes. And this will help you out a lot. Trust me, this will help you out a lot. Okay. So V minus 0 divided by 60. Again, this is the outgoing current. Again, from this node, I will assume another outgoing current. V minus, what is the potential? V1 with respect to ground, divided by 10. So plus V minus V1 divided by 10 plus V minus V2 divided by 20. So this will be 6 and 3, 9 and 10. So 10V by 60. On the other side, this will be V1 by 10 plus V2 by 20. If I multiply by 6, right, on both sides, or yeah, if I multiply by 6 on both sides, this will be, I can take 10 common, right? I can take 10 common and I can and this 6 also can be multiplied here. Sorry, 60. This will be V1, 2V1 plus V2. Sorry, actually, this will be, yeah, 6 by 10, 2V1 plus V2. I hope you know how to do the simplification, right? So what I have done, all I have done is I have taken 1 by 10 common. If I take 1 by 10 common, I have done it better. I have taken 1 by 20 common actually. If I take 1 by 20 common, this will be 2V1 plus V2. That will be certainly there, right? And this is 1 by 20. So this thing will be cancelled actually. This will be 3. So this will be 3 by 10. Sorry, this will be 3 by 10, not 6 by 10. 3 by 10. Just a bit of mathematical manipulation. That's all. Now this is just a constant number. So ultimately your V is proportional to 2V1 plus V2. And my power is proportional to V square. So your power would be proportional to 2V1 plus V2 whole squared. That is present in option C. So option C would be a correct answer. That's how simple it is, right? Okay, now we will come with the easy questions. Just let me drink a bit of water. So let's begin with this first question. They're asking me the current flowing through the 7 ohm resistor between the points P and Q. So whenever they are asking you the current through a particular branch, always use Thevenin's theorem. Although this is chapter 1 where we do basics, you can solve using basics as well. I will solve using basics as well. But always, whenever you have to find out the current through a particular branch or through a particular resistor, always try to use Thevenin's theorem. I know you are revising, so you already know what is Thevenin's theorem. So what is Thevenin's theorem? Thevenin's theorem tells me that if I remove this load, right, and if I only see the circuit without the load, then this whole circuit without the load would be equivalently represented with a voltage, Thevenin voltage, and a Thevenin resistance. Similarly, there is a Norton equivalent of this, that is just converting this into current source. Not getting into that right now, only we are discussing about Thevenin's theorem. And then obviously you will connect your load back, that is in this case, in our case it is 7 ohms. Now how do I compute the VTH and the RTH? RTH is pretty simple. Remove this load and just nullify all the independent sources, that is make the current source independent. Remember, independent current source equal to 0 and the independent voltage sources equal to 0. I hope you know what do we mean by independent and dependent sources. So if current is 0, independent current is source is 0, I0 basically means this is open circuit, right? So this particular branch can be removed, the circuit will be left out like this. I will have the 3 ohm here, 3 ohm, 2 ohm. I don't have any voltage source. If I had a voltage source, I would have replaced it with short circuit. This would be this would be 6 ohm, this would be 2 ohm. Okay, and from these 2 points I'm computing the equivalent resistance. Pretty simple, right? So these two are in series, these two are in series, because what happens, this branch was gone, so that's why this is 5 parallel with 5 parallel with, okay, hold on, this point is also connected. Okay, don't forget this, these 2 points are also connected, not that simple. Okay, these 2 points are also connected, actually don't miss that point. So now it's pretty simple. So these two are in parallel, these two are in parallel, right? So if these two are in parallel, what will happen, this will be 6 parallel with 3, that is nothing but 2 ohms. It's pretty simple, you can do the calculation. 2 parallel with 2, it will be nothing but 1 ohm. And then ultimately I have this point A and B. Between A and B I have to compute the equivalent resistance, that is RTH, that is 3 ohms, right? Because this point was simply shorted. So RTH is 3. What about the VTH? So VTH is pretty interesting. VTH would be the open circuit voltage when the load is not present. Basically when the load is open, right? So VTH would be, now you will not obviously nullify the sources. Sources will still be present. This was 5 amperes. So this would be okay. How do I solve it? So I will have to compute the voltage VAB. I will have to compute the voltage VAB. Okay. So again I can make these two in parallel, that is not a problem, right? So these two resistors again are in parallel. So again this is not a problem to us, right? So here I will have the equivalent, that will be 2 ohms, and this will be 1 ohm, right? And this is the current source. Am I correct? So these two are in parallel. Yes, these two are in parallel. Yes. So this will be 5 ampere. Now, how do I compute the voltage VAB? So we see that there is no current through here, right? There will be no current through here. So this will have no current, zero current. So the drop will be 0. So this node potential will be same as this point potential, right? So let's name this point as X. And what is the current through here? All the current, right, will flow through this resistor only. Correct? All of the current will flow through this resistor only. That is uh, 5 ampere, right? So this whole 5 ampere will flow through this resistor. because there is no other path, right? Current has to flow while there is a path. So the voltage VAB would be same as the voltage VXB. Why? Because the drop across this resistor is 0. That's why your VAB will be equals to VXB, that is equals to 5 volts, that is equals to VTH, right? So your VTH is 5 volts, your RTH is 3 ohms. So now you can very easily compute the current I. I would be equals to VTH by RTH plus 7, that is RTH is 3, so it is 10, that is 0.5 amperes, right? So that is the current through this resistor, right? Now without this VTH and RTH system, still you could have been able to solve it. How to solve it? Without any RTH VTH funny business. So you will simplify the circuit. You will certainly simplify the circuit, right? Again, these 2 points, right? These two resistors are always in parallel, correct? So again, let me simplify the circuit. This will make 3 and 6 in parallel, that will be 2 ohms. How they are in parallel? Let me mark this point as A. So this point is also A. So between P and A, how many resistors do I have? This one and this one. Between Q and A, how many resistors I have? This one and this one. So they are in parallel. So this will be 1 ohm, 7 ohm. This will be 5 ampere, right? Now you can very easily compute this current I, right? Although this question is very simple, right? With VTH and RTH it seems a bit difficult, but yeah, it depends which option you choose, right? How to simplify the circuit. So how to compute the I? Simply use the current division rule. What is the current division rule? Current division rule would be 5 into the opposite resistance. So if I have to compute the resistance, if I have to compute the current through this resistor, I will write the opposite resistance 1 divided by the total sum of the resistance, right? Which is 2 plus 7 plus 1, that is 10. So I hope you know current division rule. If you don't know, search in YouTube CDR, current division rule. You'll get the idea. So this will be 1 by 2. So this was a 2-line question. Okay. VTH RTH is very big, but mostly this will always bail you out whenever you're confused, right? Nothing clicks, no simplification clicks. Then always use VTH and RTH. If of course you are able to simplify the circuit, then obviously choose that. Let's solve this question, right? Just give me 1 second. Yeah. Consider the circuit shown in the figure. The value of VO would be equals to what? What is the value of VO, right? So in this kind of questions, just be very neat and clean. So I know the current from this node is 6 milliamperes on this side, and this is 8 milliamperes. So of course the current here would be, sorry, this side it is 2, this side it is 6. So current would be, has to income, like, sorry, here the current should be incoming, that, and the amount of the current would be 8 milliamperes. Otherwise your KCL will not be satisfied. Simply satisfy the KCL. So this current is 8 milliamperes, this is 6, this is 2. Now current here is 6 milliamperes, that is fine, 6 milliamperes. What is the current through this resistor? Remember what have I told you initially of this lecture, that if VO is in volts, your resistor is in kilo ohms, the current would be what? Voltage by resistance, VO upon 1 kilo, that is milliamperes. So remember, although here I am writing VO and the direction of the current, I hope you know why is the downward, because it should be incoming to the positive terminal. So this will be in milliamperes, although here I am not specifically telling you, right? But this will be in milliamperes only. Now if the current from here, this node, it is outgoing VO, from this node it is outgoing 8 milliamperes. So again applying the KCL, this node should have a incoming current of 8 plus VO, right? It is in milliamperes, I know that. Now here incoming current is 6, outgoing is 8 plus VO, so outgoing here should be 2 plus VO, right? And this makes sense because hold on a second, this is 6, sorry, this should not be out, this should be like this, right? Because if I add these two currents, then I will get 8 plus VO, right? Simply apply the KCL rule. 6 milliamperes incoming, 2 plus VO is incoming. So total incoming current is how much? 8 plus VO. What is the total outgoing current? 8 plus VO. They should match. Okay, and it makes sense here as well. If you see, VO is incoming, 2 is incoming, so outgoing should be 2 plus VO. So now you know currents, right? What you do? Never apply a KVL here because there is a current source. Never apply a KVL here because there is a current source. You don't know what is the voltage across the current source. That is unknown for you. You know what is the current through this voltage source. Good thing, great thing, right? You know the current across this voltage source. So we will only apply the KVL in this loop. That will only help us to compute VO. This will not help us to compute VO. This will not help us to compute VO because the voltage across the current source is not known and it can be any value. So needlessly, you will just increase your calculations and number of unknowns. So don't do this. So compute here, right? So if I compute the KVL here, this will be again the same thing. Current here is incoming like this, right? So this will be plus, this will be minus. So plus, because I'm encountering the positive sign first, plus 1 into 2 plus VO. Minus 4 plus VO equals to 0. So this would be 2 VO. Equals to 2. One volt. So V is equals to 1 volt. So now yeah, so we okay, this is the answer. We got our answer. I'm thinking what to do next. We got our answer. So V is 1 volt. This is your answer for the question. So that's how you solve this question in a simple manner. So yeah, let's solve the next question. Yeah, this question is great. So we will solve this question certainly, but before solving this question, let us try to break this question up, right, into easier parts. Okay, no, not this question, sorry, this I thought it was no. This one is pretty simple. So we have to find out the current I in the circuit shown. What is the current I, right? Pretty straightforward. Again, everything is in kilo, so I don't need to write in amperes. I will write my current in milliamperes. So this will be 1 milliamperes, that is incoming. This I current is also in milliamperes. That is my assumption. So what is the current here? Outgoing current would be I plus 1. So I plus 1 into 2. So now let us apply the KVL. Again, I will not apply the KVL here because there is a current source and I don't know the voltage across the current source, but I know the current. I know the current across the voltage source. So I will always apply the KVL here, right? So this will be minus 5 plus 2 into I plus I plus 1 into 2 equals to 0. So this will be 4I equals to 3. Remember, your I is in milliamperes. So this will be 0.75 milliamperes. That is 0.75 into 10 raised to the power minus 3 would be your answer for this question. Pretty straightforward and simple. Just you will have to apply the KVL in the voltage source, not in the current source branch. This one, this question is pretty good, right? So they are simply asking you what is the current flowing through I. Like, this question is actually simple, but this question would have been pretty good if they would have made few modifications. If you see here, we have a ground, right? So let me solve it for the easier case. Let's say there is no ground. How will you solve? What will be the value of the current? Just remember this simple rule. Whatever current that goes out of the battery, let's say this is some Ix current. From the positive terminal, the same current should enter in the negative terminal. So this should be equals to Ix only. This shall not change. So current from here is Ix. It is in series, right? So current here is Ix incoming at this node. Again, current here is Ix. Again, current here is Ix. Again, current here is Ix. And I know the KCL should be valid, that sum of all the incoming nodes should be equals to outgoing nodes. I don't know what is happening. Like, I'm getting too much. I have to break my recording in between. Too many calls from HDFC. They're just providing me free loans, pre-approved loans. Le lo jitna loan hai. I just don't understand this. Sorry for interrupting the class. Just too many calls. Yeah. So yeah. So whatever is the, if I apply KCL at this node, right? This will be Ix incoming current would be equals to outgoing current Ix plus I. So actually your I comes out to be 0. Same thing if you do here, you will see the same thing, that let's assume the current that leaves from the battery is Iy, enters is also Iy, it has to be the same current. So again, current through here would be Iy, current through here would be Iy. Again, if you apply a KCL at this node, you will see your current comes out to be 0. So what is the conclusion? The conclusion is, if there are no grounds, if they have given you no grounds, then you are very safe. If they have given you no grounds are given, right? If no grounds are given, and if you have two networks, network A and you have another network, network B, and it is known that there is no ground, right? In these two networks there is no ground, and if there is a wire connecting the two networks or a resistor connecting the two networks, there will not be any current flow here. Why? Because there is no possible path for return. There is no possible path for return. If only a single resistor is connected, if the current goes like this, there has to be a return path, right? If there was a connection here, then certainly there would have been a return path, then certainly this current may be non-zero. But whatever will be this current, the same current will be coming from here. This will be the same I current. Because there are no grounds. Okay, I will come to the case where there will be grounds. But let's for now discuss whenever there is a ground. Sorry, whenever there is no grounds given in the question. So that is the thing. If I just connect like this I current will always be 0, because though there is no return path. But now if I copy the same thing and let me reduce the size, I connect a resistor here R2, and again the same condition, that there are no grounds. So whatever is this current, right, I, that goes from network A to network B, the same current will come back in I only. That is the beauty. Why? Due to this property, because this battery still should have the same current. So you will apply KCL here, you will apply KCL here, and you will realize that your I will come out to be the same value whatever it was coming out to be at this particular node through this particular resistor. So whatever the value of resistor, it does not matter. The current value will be same as this. These two currents will always be same if there are no grounds connected. Now let's slowly increase our complexity. If there is a ground connected here, what will happen? If there is a ground connected here, pause the video and tell me, will this current be 0 or will it be not 0? Pause the video, honestly pause the video and tell me. So if we said it will be non-zero, you are wrong. Congratulations, you are not listening to my lecture. So again, let's go by basics. What is the basic? Basic is, whatever the current that will leave from the positive terminal of the battery, same current should come into the negative terminal, Ix. So this current is Ix. Now this current is Ix. Now if you say this current is also Ix, you are somewhat wrong. Why? Because this ground can also have any current, right? We don't know what is the current here. So I will not be able to comment what is the current through this wire because there is a ground connected as well. Some current can flow into the ground as well, right? So now let's try to analyze this particular branch, this particular loop. This is pretty simple. This is IY. Here the current is IY. So this current should be IY. This current should be IY, right? There is no ground, there is no worry. So certainly if I apply KCL at this node, my I will be 0. And if I is 0, then this current also will be Ix only. So this current also will be Ix only. So actually the current to the ground is actually 0. Right? I will conclude everything. Don't worry. I will conclude everything. So again, if there is a ground connected to the one of the networks, right? Even if there is a ground connected to one of the networks, still the current will be 0 if there is no return path. Don't worry. I will conclude everything. So let's say ground is connected here. The current will be 0. And they will ask a good question from this. Don't worry. I'm expecting they will ask a good question. Now, the opposite case, if a ground is connected here, again, same thing, nothing will change. Current again will be 0. If the ground is connected here, current again will be 0 because there is only one ground connected, right? So actually for this question, you're done because there was only one ground connected. So you know the answer would be 0. But let's come to this point. Let's come to this point. This is the interesting point, right? And I'm expecting they will ask question using two grounds. In this case, will it be 0? No. This is not your question. Your question is done. Your answer is 0, right? I'm talking about what will happen next time. Next time when they will ask this one. When there will be two grounds. Now, if there are two grounds, this current will not be 0. Why? Because there is a return path between the networks. How is there a return path? Because these two points are at 0 volt potential, same potential, and we know same potential points can be connected, they are equipotential. So technically whatever current that will go, right, there is a return path from the network. The same current I will flow back like this, right? So it is the same picture. This picture is the same, but the difference is this time there is a return path through the ground because there are two grounds here, right? You will say, how do I know? So if nothing is given, you will not assume these grounds, right? If nothing is given, you will just see whatever is given in the question, accordingly you will solve. If there are two grounds, they will show you the grounds or tell you somehow, right? They will tell you somehow, right? This will be given. So if there is only one ground connected, that means there is only one ground connected. You don't assume a ground here, right? If there is a ground, they will tell you, right? So in this case, pretty interesting, right? If two grounds are there, so there is a return path, so there will be some current that will flow. How do I calculate the value of the current? Pretty simple, right? What you can do, is, you know, this is 3 volts, right? And this current, let's say some I1 current. This current also will be some I1 current, or let's say this is Ix current, right? Living from the 3 volt source. This will be 3 Ix, but this will not be Ix. This will not be Ix anymore. Why? Because there is a current I that is coming back at this node, right? What is happening? If I just remove the two grounds, essentially these two are just connected. So this I current is incoming here, right? So this I current is incoming. So there is a I current that is incoming at this node, and there is a Ix current that is outgoing. So what will be the other current, other incoming current, right? So the sum of the two incoming currents, Ix. So what is the outgoing current? Ix, right? What is the incoming current? Let's assume this current is some I1. So I1 plus I will be equals to my outgoing current, right? This is the overall incoming current. equals to my outgoing current according to the KCL. So these two resistors are not in series anymore. They are not in series because this current is I1, that is different to this current Ix. Again, this current will be again something else. Right? What will be this current? Let me assume this current to be Iy. This current is Iy. In this case, this current is outgoing. This current is also outgoing. So here the incoming current would be Iy plus I. Right? How, like, so you know the currents across all the branches. So there are many ways to solve this question. You can apply a KVL in this loop. Right? You can apply a KVL in this loop. After applying the KVL, you will be able to find out the value of Ix, I1, I, everything. You can do it, right? So I can show you as well. Let's apply the KVL. Let's apply the KVL in this loop, right? Loop basically means I will start from a point and I will come back to the same point. Correct? So if I apply a KVL in this loop, what will be the value? This will be minus 3 plus Ix into 1 plus 10I just give me a second. Okay, plus 2 into, now remember what is the direction of the current? Direction of the current is like this, so voltage drop is plus minus, no problem. But here the direction of current is like this, so voltage drop is, it should always enter the positive terminal for a resistor. So but I'm applying my KVL in this direction, so I'm encountering negative sign first, right? So I will write the negative sign first. So this will be minus, this will not be plus, this will be minus 2 Iy plus 3. I'm encountering positive sign, and then again we're coming back to the same point basically, right? So this is equal to 0. So from this we got one result, that Ix minus 2 Iy, or yeah, Ix minus 2 Iy is equals to minus 10. This is one equation. And what about the other equation, right? Okay, so from this we know what is my I1. I1 is equals to Ix minus I. And now I know what is my Iy. Hold on a second. So, oh sorry, this current is, the current through this resistor is simply Iy plus I. That is fine, right? So if I apply, so this drop will be what? This drop will be plus minus like this. Now if I apply a KVL in this loop, what will I get? So we start from here. Again the drop will be something like this, right? Because the current is flowing like this. So this will be 2 into I1 minus, because I'm encountering a negative sign first, because I always go in the clockwise direction. Again this direction is fine, that is plus 10 into I. Now you will not actually, the thing is, you will not do all this. So this is all redundant, right? What have I told you? Like you can solve it like this, right? But this will take you a long time. I'm just showing you a bit of trailer that how much lengthy this can go. But there is an easier way to solve. What have I told you? Whenever you have to find the current through a particular branch or a resistor, always try to use Thevenin's theorem. If I use Thevenin's theorem, what will happen? That this circuit will be reduced. So if I first I will remove the load and I will calculate the open circuit voltage. Now it's pretty simple. If I see the open circuit voltage, this is 1 ohm. This is 2 ohm. And this is 1 ohm, 2 ohm. This is 3 volts. This is ground, right? This is 3 volt ground. So I have to compute the voltage at this point A and compute the voltage at this point B, and my VAB, the open circuit voltage, would be my Thevenin voltage, right? That is VA minus VB. So what is VA? Very simple, the potential with respect to ground. So these two are in series. Now it become very simple, these two are in simply series. So this voltage will be simply 2 volts, and this voltage, according to the voltage division rule, will be 1 volts. So VAB would be equals to 2 minus 1, that is 1 volt. So VTH is 1 volt, pretty simple. What about RTH? RTH will face a bit of difficulties. So RTH, we'll have to short this. So this will be shorted. Voltage source will be nullified, that means short the voltage sources, that means V equal to 0, and this should be shorted. Now don't forget to put the grounds. This will be 1 ohm, this will be 2 ohm, this will be 1 ohm, this will be 2 ohm. Now what is happening? If I assume this to be point A, this to be point O, this to be point O, this to be point B. So between A and O, 1 ohm and 2 ohm are in parallel. Between A, B and O, 2 ohm and 1 ohm are in parallel. Now these 2 points are the same O points. So actually I can connect these 2 points. So this will be what? This will be 1 into 2 divided by 3, that is 2 by 3. That is my point A. And my point B is also 2 by 3 ohms, 2 by 3 ohms. And this is my point O, right? Which is grounded, which does not matter. Ultimately, what I have to compute? I have to compute the RAB. It's very simple. These two are in technically series. Although this point is grounded, you are correct. This point is grounded, but there will be no current through this ground because I am connecting my voltage source like this, right? That's how we compute the equivalent resistance. So whatever current will come, same current will go out here because I'm connecting a battery here, right? Because we're computing the equivalent resistance. This positive current leaves from the battery, same current would enter into the battery, right? So I current, same I current. So there is no current through the ground. So there should not be any doubt in your mind what is happening to the current in the ground. So all these things we are clearing. So if you are enjoying this concept, put a comment down below if finally this question is cleared totally in your brain. And yeah, like the video, hype the video, like we have to do marketing in between, right? So yeah, so these two will be in series because there is no current going through the ground. So 2 by 3 would be 4 by 3. Ohms. So 4 by 3 ohms is the RTH and VTH is 1, right? So 1 volt, 4 by 3 ohms, and the resistor value is 10. So now you can easily compute the current. It's very simple, 1 divided by 4 by 3 plus 10, that's fine. But if you try to do it like this, right, it will take you ages. But in exam, we don't have ages, right? So that's why I have told you, always try to go with Thevenins whenever you're confused. Here I was starting with this just to show you how tedious the calculation can become, right? Always avoid that. So let's, now most of the questions are pretty simple, cakewalk for you. It should not be much difficult for you, right? So in the circuit shown below, the current I flowing through the 200 ohm resistor is. So we have to simply find out the current. So it's pretty simple and straightforward. You can apply a nodal KCL at this particular node, right? So if I apply KCL at this node, the incoming current is 1 milliampere. Then outgoing current is also 1 milliampere plus, let me assume the voltage here to be V. Let me assume this to be my ground. So V minus 0 divided by 1, again everything is in kilo. So current is in milliamperes, V is in volts. So no problems. Plus, okay, I don't know what is the potential here, right? So this will be, so do I know the potential here? If this current is I, now this is written in 200. I want to convert this in kilo ohms because everything is in kilo ohms only. So this will be 0.2 kilo ohms, and the current I know, that is I. So the voltage drop would be 0.2 into I, that's all. So it will be, this point potential is 0.2 into I. So V minus 0.2 into I divided by 1 kilo ohm. Okay, so we have written this note, this particular branch, this particular branch, this particular branch, this particular branch is not done. So this is V minus, okay, sorry, this will be not V1, this will be 2, right? Because this is 1 milliampere current entering, this will be V minus 0 by 2, sorry, 2 ohms, right? So this should be 2, sorry for that. And this will be V minus 2 divided by 2, because the potential difference here is 2, right? I hope you know how to take the KCL. So V minus 2, right, divided by 2, because this point is plus 2 with respect to the ground and there is a 2 ohm resistance connected. That's why the potential difference across this resistor would be V minus 2 and the current would be V minus 2 divided by 2 kilo ohms. This will be equals to 0. Now if I, okay, solve this particular thing, will this help me? So that will go away, V by 2, this will be V, this will be 2V minus 0.2I minus 1 equal to 0, right? So V is equals to 0.2I plus 1 divided by 2. So that is my V. Now let us apply the same KCL at this node. That would be, what is outgoing current? I. Incoming current 1 milliampere minus 1. And incoming current of what? So this would be basically, I know the potential here, right? That is 0.2I. So the potential is 0.2I. 0.2I minus V divided by the 1 kilo, right? 0.2I minus V divided by the 1 kilo ohm equal to 0, because ultimately there are only 3 branches. So there is a concept of super node, super mesh. I don't want to get into that. I don't want you to remember things needlessly. It's fine. It will take you 10-20 seconds more, but your brain needs to remember other things as well. I know you guys will be able to solve this using super node, super mesh concept. I do know that. But if you remember all those things, then when will you remember your core subjects? Right? So you will have to take some space out of your brain as well. So this will be I minus 1 plus 0.2I, and I know what is my V value. V value is this, right? So this is 1.2I minus 1 minus 0.2I, sorry, minus 0.1I minus 0.5 equal to 0. So this will be 1.1I equals to 1.5, right? So your answer would be I would be equals to 1.5 divided by 1.1. Remember, all our units were in milliamperes and they have asked in milliamperes only, so you are safe in that zone. So let me just quickly divide this value. 1.5 divided by 1.1, that comes out to be 1.36. So 1.36 would be your answer for the question, answer of this question. So let's solve the next question. So again, a simple combination of KVL and KCL. They've given, they have asked us to find out the value of Ix, right? And if these are the values, now there is a dependent source that depends on the value of IO. So whenever something like this happens, right, just be very careful. Okay, be very careful actually in this case. Okay, because don't assume your IO to be in milliamperes, because they are using this IO somewhere, right? And if nothing is mentioned, by default you will assume your IO to be in amperes. Why? Because they should have probably mentioned that what is the unit of IO that they are using over here. But if nothing is mentioned, by default you will assume your IO to be in amperes. Now if your IO is in amperes, right, things become a bit difficult, because all these values milliamperes, right? So then you will solve using amperes only. You will not go by milliamperes. You will solve using amperes only, because this IO is getting used here. Why? You will mess up something at the end if you convert everything into milliamperes. That is the reason why I am saying like this. So this is 2 milliampere, this is Ix. Let's assume Ix is in milliamperes. There is no problem with Ix, right? Ix can be in milliamperes only. So this current would be what? This current would be 2 plus Ix in milliamperes, because Ix current we can assume it to be in milliamperes because it is not getting used anywhere else. So I am safe there, right? And what is the current here? So this is the outgoing current, right? That is 2 plus Ix in milliamperes. This is the incoming current. So 5 milliamperes equals to the outgoing current, that is IO, that is in amperes, plus 2 plus Ix in milliamperes, right? So now this is in amperes, so I will not do anything with this, but these are in milliamperes, so I can play around with these values because these are in milliamperes. So your IO is actually equals to 3 minus Ix in milliamperes. Okay, be very careful, this is in milliamperes, remember this is a unit, this is in milliamperes, right? Now what I will do, again I cannot apply KVL here, current source, I cannot apply KVL here, current source, I can apply KVL here, no current source, right? So if I apply KVL here, again current is flowing like this, plus minus, current is flowing like this, plus minus. So if I go in the clockwise direction, first I am encountering negative terminal, so minus IO into 1 kilo ohm, right, 1k, minus 1000 IO, and then plus Ix into 1k equals to 0, right? Now remember, if there is a 1 kilo ohm multiplied, I can replace my IO with milliamperes. Milli into kilo is unitless, it is 1, milli into kilo is 1, so minus IO into 1 kilo, so this will be actually minus IO is what? IO is this value, right? 3 milliamperes, so I'm already replacing it with milliampere. 3 minus Ix, where Ix also is in milliamperes only. Okay, Ix already is in milliamperes only, minus 1000 IO, or okay, let me keep the IO, okay, let me keep the IO for now, right? Let me keep it, this is 1000 into IO, right? So 1000 IO is already here, 1 kilo is 1000 IO, so this will be 2000 IO. I can take it on the other side, right? So if I take it on the other side, so 2000 into IO would be equals to, so what is my IO, right? IO is this milliamperes, so let me write the units properly. This will be 3 minus Ix is in milliamperes, right? Okay, hold on a second. Okay, I have written the KVL here, right? So this will be, all these are in milliamperes, that is 10 raised to power of minus 3, right? And okay, this is IO. So from here I can directly say what is 1000 into IO. 1000 into IO is equals to 3 minus Ix. 1000 into IO is equals to 3 minus X. Okay, cool. Now just let's replace this, right? This is easier for us. Now this is in milliampere, this is in milliampere, right? This is 3 minus Ix is already in milliampere. I've written this, I converted this into amperes, right? Into 10 raised to power minus 3. So this is proper right now. This was in milliamperes. All I have done is I've just written the milli properly to in amperes, so that the left hand side IO is in amperes, right hand side also can be in amperes. So then if I equate these things, 1000 IO becomes 3 into 3 minus Ix. But remember, these two values are in milliamperes only, right? Don't worry, these are in milli, so these are proper. Don't worry about it. They are proper already because I've already taken care of this conversion, right? So 2000 IO is equals to 2000 IO is equals to Ix into 1 kilo, right? Ix into 1 kilo. Ix into 1 kilo. Now Ix is already in milli, right? Kilo into milli will be 1 only, right? So 10 cube into 10 raised to the power minus 3. What is it? It is 1 only. Let's assume that Ix is equals to 2 milliampere. So 2 milliampere into 1 kilo ohm. What will be the value? It will be 2 only, right? So I will, that's why I am writing simply Ix only, right? So Ix, now what is 2000 IO? 2000 IO is basically 2 times this, right? So that is 6 minus 2x, that is Ix. So 3x is equals to 6. So Ix is equals to 2 milliamperes. Remember, your Ix was in milli. It was in milli. So Ix is 2 milliamperes. So what will be your IO? Ix is 2 milliamperes, right? So IO would be 3 minus 2, 1000 into 3 minus, okay. Okay, you anyways have to only find out Ix only. You don't have to find out IO. So your job is done, right? But yeah, your answer is this 2 milliamperes. But you can extend this. Certainly you can extend this, right? Your IO would be basically 3 minus 2. That is 1 divided by 1000. Remember, your IO was in amperes, right? Your IO was in amperes. Correct? This value. So in milliamperes, it would be 1. Got it? So there should not be any confusion in the units. So for this question, the answer would be 2. So yeah, let's begin with solving a few gate PYQs from double E branch. So this is the first question. In the given circuit, Vy is 0. This node voltage Vy with respect to the ground is 0. The value of beta should be what? What should be the value of beta? So Vy is given as 0. So okay. So for calculating beta, I will somehow need Vx. So let us actually calculate Vx. How? Let us apply nodal here. If I apply a nodal here, right, this will be Vx. Just give me a second. Vx minus 6 divided by 1. Vx divided by 4. Now plus Vx minus Vy divided by 2, and Vy is 0. So it will be Vx minus 0 divided by 2. These are the 3 branches, right? This will be equals to 0. That is the KCL, a nodal equation. So this will be Vx. So 4 plus 2 plus 1 Vx divided by 4, 6 equal to 6. So yeah, this will be Vx equals to 6 into 4 divided by 7. Okay. So yeah, Vx value is this. Now let us apply a KCL at this node. This node potential I know 0. That will be very useful to me. So this will be basically 0 minus Vx. Vx is what? Vx is this value. So let me keep Vx for now. I will solve it later. I will put the value later. Divide by 2. That is the KCL here. Plus Vx minus beta into, sorry, Vy, that is 0 minus beta into Vx divided by 3 plus, now remember, it is an incoming current, right? And I show incoming current according to my convention as negative 2. So this will be minus 2 equal to 0. So from this, we can actually get the value of beta. Beta would be equals to minus Vx by 2 minus 2 into 3 divided by Vx, right? I'm just doing some manipulation, that's all. So this will be actually equals to minus of 1 by 2 minus 2 by Vx, right? What is 2 by Vx? So 2 divided by Vx is 6 into 4 into 7, and of course we have multiplied by 3. So this will be minus 3 by 2. This 3 will be cancelled, minus 7 by 4. So this will be basically minus 6 minus 13 divided by 4. That is what my beta is equals to, right? Let me just quickly check. This is 0, negative 2 current, 0 minus beta into x, 0 minus Vx, incoming current, okay, This beta will go on that side, this will be negative. Okay, this should be negative. What is your Vx? Let me just quickly check. Your Vx divided by this, 6 will go on that side, right? Vx minus 6, Vx divided by 4, Vx minus 0 divided by 2. Okay, everything is correct here. This will go on that side, this will be divided with the Vx. Three. Okay, so minus 13 by 4. So in this case, what will be the answer? 13 by 4, that is minus 3.25. This will be the answer of this question. So yeah, let's move on to the next question. This is the next question basically. So here we have, in the circuit shown below, the magnitude of the voltage V1 would be, so basically they're asking me the magnitude of the voltage. Simple KVL KCL again. So if this voltage is V1, right, what is the current? I know the current would be V1 divided by 8, right, in milliamperes, because 8 is in kilo ohms, right? That's why it will be in milliamperes, right? So your I current is actually equals to V1 divided by 8, although it does not matter much, but that's fine. Okay, so this current is V1 divided by 8. Okay, it will matter because this is my I current, right, and it is a dependent source here. I hope you know what is a dependent source, right? Although I have not talked about it before that, but it is understood that you know what is a dependent source, right? Dependent current source, dependent voltage source, you know these things, right? Like if I have a current here I, so this current across this particular source will depend on this current, right? So it will be I only. Sometimes it is 2I, 3I, like that. So although I have not mentioned this previously, but I thought you might be already knowing it because it's a very simple thing, and you study this as the first thing that when you start studying network, right? So yeah, so this will be I, and this current is also I, right? Both of these currents are I, so current through here is actually 0. Current through here is actually 0. Good to know, good to know. Okay, now what I can do is I can apply a KVL in this loop because I always avoid current sources when I try to apply KVL, right? If I have a current source, I will always try to apply KCL. I will never apply KVL. Why will I never apply KVL? Because the voltage is not known across the current source. The voltage is not known across the current source. That's why I will avoid KVL at any cost. That is my last resort, right? I can apply KVL here because everything is voltage, no problems. So this will be minus 75 plus 2 into I, right? This is plus minus, I current is going like this. I is in milliamperes, plus 0.5 V1 because I'm encountering the positive sign plus, equals to 0, right? So yeah, now uh, uh, yeah, now this would be, I know what is my I, right? I know what is my I is V1 by 8, 2I would be V1 divided by 4. So simply just change it. So minus 75 plus V1 divided by 4 plus V1 divided by 2 equal to 0. So this would be 3V1 divided by 4 equal to 75. So V1 would be equals to 100 volts. So V1 value is equals to 100 volts. This will be an answer for the question. Pretty simple, pretty straightforward, right? Nothing much to worry about. Let's solve the next question. So all you need to know is just dependent sources. That's it. For the circuit shown in the figure, V1 is 8 volt DC, I1 is 8 amperes DC. The voltage VAV, this voltage across the resistor would be what? Okay, so this current is 8 amperes, right? 8 amperes is incoming at this node. This voltage is 8 volts. Okay, okay. Now if you notice one thing, let me mark this point as C and let me mark this point as B. This point is already marked as B only, right? Now between this C and B, I see what is the potential. This is also B, right? The potential is 8 volts V1, and that is actually, okay, no, that is not actually connected across this 2 ohm. But we can do bit of simplification. This point is B, right? So these two are essentially in parallel, correct? And this point is B. This point is, let's say, point D. So between D and B, this 2 ohm is in parallel and this 2 ohm is also in parallel, correct? So I can simplify this circuit further. This will be 3 ohm in parallel. This will be 3 by 2. This would be 1 ohm, right? I hope you know how to do the parallel. So these two things will be parallel. This will be still my B point, right? And this will be my E point, about which I will have to compute the VAB. And this is still here, 0.5 ohms between C, and still I have the current source, that is 8 amperes, and still I have the voltage source. Okay, now it is much simpler, right? So this is my D point, correct? This was my AB point and this is my D point. Now we simply know, like, these two are in series. Technically these two are in series. So what will happen? So basically there will be voltage division, right? So it will be 8 into 3 by 2 upon 1 by 2 plus 3 by 2. This is equals to 8 into this would be 3 by 2 upon 2, that is 3 by 4, that is 6 volts. So your VAV would be 6 volts, right? Although you will say, sir, you have simplified, you have changed the circuit. Yes, I have changed the circuit, but these two node points are still the same, right? All I have to do is calculate the voltage between these 2 points. So what I have done, I know the voltage VCB. VCB is how much? 8 volts, right? And we can see after resolving the circuit, simplifying the circuit, these two are in series. If they are in series, simply I can use the voltage division rule. Voltage division rule says to me that the current is same. I can just use this, right? What is voltage division rule? Look it up. Just look it up, right? It's very simple. Current is in series, so you will multiply the overall voltage into the resistor upon the sum of the resistors. Very simple. Just look it up. Look up the voltage division rule. You will understand it. So answer for this question would be 6 volts. Let's now move on to the next question. Now this question is pretty interesting. So here they're asking me what is the number of junctions in the circuit. Now many students would say they will use some formula, but actually to solve this you don't need any formula to solve this particular question, right? Although I will say you one formula, but you don't need anything. So what is number of junctions? Number of junctions are those where two or more branches meet. Okay, junction is a point where two or more branches will meet each other, like this point, right? So three branches are meeting, so this is a junction point. Okay, so sorry, not two or more, sorry. So a junction, I will write here, a junction is a node where three or more branches meet. So let's take this example, right? Here I see, so what is a branch? Branch basically means elements, right? You can assume that. So branch, what is branch? Branch is basically a path. What is a branch? Branch is a path between two nodes. So it is technically a connector, right? Now what is a node? Node is basically node is made when two or more branches connect. So node is made when two or more branches meet. So the difference between junction and node is basically, here I can have 3 or more, here I will have 2 or more. So every junction will be a node, but every node will not be a junction. Make this like try to understand this point, because they can ask MSQ from this. So in this case, junction would be where 3 or more branches meet each other, right? So here 1 branch, 2 branch, 3 branch. So this is certainly a branch. What about this one? So this particular point, right, if you see, 2 branches are meeting, 2 elements are meeting, but this is not a branch. This is a node. Certainly this is a node, but this is not a branch. Okay. So here, this is certainly a branch, AB. Again, this is again certainly a branch. 3 nodes are meeting. This is a branch. This is a branch, and this is a branch. A, B, C, D, E, F, G, H, E, F, G. This is a branch. So 1, 2, 3, 4, 5, 6, 7. So there are a total of how many branches? 7 branches. And you will tick mark this and you will be wrong. Because if you look at this particular point closely, your E and D points are same. They are simply short circuited. They are the same point. So be very, very careful, right? You will just lose out on one easy 1 marks. You will get minus 0.33, right? So in exam hall, you will have to be very, very careful. Avoid making silly mistakes, right? That is the utmost thing that I want to say to you guys. Be very, very careful. So yeah, in this case, option A would be correct, because E and D are the same points. So it's a single point only. So option A would be correct for this question, right? So yeah, now there is a formula. This one, if you want to remember, but I hardly believe that they will ask a question from this. But if you want to, you can remember. So this is the number of branches. This will be the number of loops, right? I hope you know what is a loop. So this is a loop. I have 1 loop, 2 loop, 3 loop, 4 loop, 5 loops, right? So overall I have 1, 2, 3, 4, 5 loops. So overall number of loops is 5, right? And number of branches, how many branches I have? 1 branch, 2 branch, 3 branch, 4, 5, 6, 7, 8, 9, 10, 11, 12. Overall I have 12 branches, right? Now you can actually measure how many nodes I have. So 1, 2, 3, 4, 5, 6, 7, 8. Sorry, this already has been counted. Sorry, 8, 9. 9 branches, right? Okay, somewhere I'm over counting it. Just let me count once again. So one, so not how many nodes? 1 node, 2, 3, 4, 5, 6, 7, 8, and 9. No, this is, so this I think this already have counted. I have already counted A. I am guessing. So one, hold on a second. Let me count this again. 1, 2, 3, 4, 5. So hold on a second. 1. So let me mark it A, B, C, D only, or let me mark it actually. That will be the best thing. So this is already done. So let me mark it. Otherwise you will forget. 1, 2, 3, 4, 5, 6, 7, 8, 9. This also will be branch, right? So there are total, sorry, not branch, there are totally 9 nodes minus 1. So okay, just hold on, let me see if I have counted the number of branch properly or not. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. Okay, sorry, my bad. That's what I was thinking, like somewhere I'm making a mistake. So number of branches would be 13. So it's a big circuit, so things might become a bit confusing. So you can draw the circuit and then mark your points. That would be the best way to go about it. So yeah, if you see, this formula will be valid basically, and this will work. But it's not like you'll have to remember this formula. Without remembering as well, you can do it, but like it will just take you a bit more time. That's all. But this question would not require this formula, right? At a later stage, they can ask from this particular concept. That's why I'm just telling you this formula. That's all. Let's solve this question. All the circuits in the all the elements in the circuit are ideal. The power delivered by the 10-volt source would be in watts. So all the elements are ideal. So what will be the power delivered by the 10-volt source? That is what they are asking me. So this is alpha ohms, right? Okay. So what is the power delivered by the 10-volt? So let me write the KCL at this node, right? What is the KCL? This would be V minus 10, that is 10-volt, upon alpha, plus V minus 0 upon 1. I am assuming this to be my reference, plus, now this current is 10 amperes incoming, right? So minus 10 equal to 0. So your V minus 10 by alpha, this, right? This is the current delivered by the battery, right? So this is the outgoing current actually. So this will be the same current as the current delivered by the battery, isn't it? So if I am writing V minus 10 by alpha, it is this current, right? And this current would be the same in the negative direction, minus I. If you are having confusions, let me just mark the currents. Let's say this is current I, right? And this is point V. So I have assumed that my current is outgoing, but originally it is actually incoming. So I will have to add a negative sign. That's all, right? If you are ever confused, you can add a negative sign. Why? Because you're so okay. Don't add a negative sign here. Don't add a negative sign here, because this is the current, right? That you were assuming that is outgoing from here. What is this current? This will be equals to minus of I, because it is incoming. That's all, right? So okay, if you're confused, just ignore the V point. Okay, don't ignore the V point, just ignore this particular equation, right? You know this current is incoming to this node, so you will write minus I plus V minus 10 equal to 0. So your V, so your I, sorry, is equals to 10 minus V. Okay, that is what your I is equals to. Now they are asking me what is the power delivered by the 10-volt source. So power delivered by the 10-volt source will be 10 into I, the current that is outgoing. So this will be 10 into 10 minus V, because I is 10 minus V, right? So this will be 100 minus 10V. 100 minus 10V, right? So 100 minus 10V, this would be, okay. So what is V? How do I calculate the V value? So actually I can calculate the V value from here actually, right? So this is alpha ohms, this is 1, okay. So if I simplify this equation, this will be V 1 plus alpha 1 equals to, this will be 10. If I take common, this will be 1 plus alpha plus 1. So magically things are getting cancelled. Okay, If things are getting cancelled, you can say that your V is actually equals to 10 volt. If your V is equals to 10 volt, right, what is happening? V is 10. So this will be 100 minus 100 itself, that is 0 watts, right? So basically the battery is not delivering any power. It is 0 watts only. It is not delivering any power at all. How did I solve it? I assumed a node voltage here. I assumed a outgoing current here. So there can be, I can write these two equations at the same time. You should not have a problem with it, right? Be comfortable with it. Once I'm writing the current according to the node voltage. Second time I'm writing the current according to the incoming current. Why did I do this? Because I had to first of all get the value of current I as a function of V. I got this, I got the power function, and then I got to know that I need to compute V. If I need to compute V, let me actually now use this equation, the node voltage equation. So if I simplify it, right, so in examination there will be multiple times where you will feel stuck that what to do next, how to solve this, right? Just proceed with your actual method and then you will see something magical will happen somehow. Okay, most of the cases, if you have the good luck, you will see the magic. Otherwise you will just iterate over your question and you will not be able to solve it and you will be stuck. So you will have to have a good idea of skipping the questions as well, right? So this will be 10, this will be V would be equals to 10 volts, right? So yeah, this will be 0 watt. That will be the answer of this question. Let's solve the next question, right? This is the next question. The IV characteristics of the element between nodes X and Y is best depicted by what? So IV characteristics, right? IV basically means current voltage. So if I change the voltage here, right? If I increase the voltage, what will happen? If the voltage is increased across the XY point, this current, right, through the 1 kilo ohm will increase. And I know your IXY is actually equals to 1 plus VXY by 1, right, in milliamperes if you want to say, or this will be 1000 basically 10 cube, because this 1 is in amperes. So basically what is happening, this is the relation, right? So if you see your current is a linear function which has a x-intercept at 1. So we have a x-intercept at 1 and then we have a slope, positive slope of 1 by 10 cube, correct? So positive slope of 1 by 10 cube, so it will be increasing and we will have an intercept at 1 ampere. So option B would be your answer for the question. Like very basic and very simple question that they have asked in 2025. Another very simple question that they have asked in 2025 is this one. A nullator is defined as a circuit element where the voltage across the device and the current through the device are both 0, right? Voltage across the device and the current through the device are both 0. Now a series combination of the nullator and a resistor, right? So I have a nullator here and a resistor of R value will behave as what? What will be this combination behave as, right? We know the voltage across the nullator is 0. We know the current through the nullator is 0. And if they are connected in series, that means the current will be same across the resistor as well. And if the current across the resistor is 0, we know the voltage across the resistor is also 0, right? V is equals to IR. So overall the voltage across this whole element is what? 0 plus 0 is 0 only. What is the overall current that is incoming to the combination? 0 amperes. So 0 volt 0 ampere, that is nothing but a nullator itself, right? Because nullator is a circuit element that is defined where the voltage across this device is 0 and the current is also 0. Hence nullator would be your correct answer for this question. Like pretty basic question. With this we are done with the basics. We took almost 19 questions, right? Now we will begin with network theorems. Let's begin with network theorems. So first we will do BM-PYQs, then IN, and then EC, and then EE. So this is the first question. If the circuit shown below Vs is equals to 100 volts and R1, R2 are this, R3 are this, right? R5 is this. The current flowing through the R3 resistor would be. So if you notice one thing, R1 into R5, right? Because this is just a bridge, right? let's see if the bridge is balanced. R1 into R5, so 30 into 30, that is 900. R2 into R4, R2 is 60, R4 is 45. So what is it? 6 into 45, so 6 into 240, 240 into 630, 270. So it is like these are not certainly same, right? This multiplication, cross multiplication is not same. So certainly the bridge is not balanced. 60 into 45, R2 into R4. Yeah, that is 2700, and 30 into 30 is 900, right? 30 into 30, R5, yes, 900. So basically, I hope you remember the bridge balance condition. So the opposite ends, if I multiply them together, the product must be same. That is R1 into R5 should be equals to R4 into R2, and then we see the bridge is balanced. The opposite end resistor, if I multiply these two, the bridge is balanced. And if the bridge is balanced, that means the current through the diagonal resistor would be simply 0. Diagonal element will be 0 if the bridge is balanced. Very basic concept of Wheatstone bridge, but in this case the bridge is not balanced, so current will not be 0. Then how to compute the current? Use basics, VTH, RTH, right? Whenever you will have to compute the current through a particular element, use VTH, RTH, Thevenin's theorem. So if I open the load, this will be R1, R2. What is VS? VS voltage is 100. R2, R5, R1, R4. So this, let's assume this as reference. So the voltage VTH, open circuit voltage, would be what? Simply apply VDR, voltage division rule. This voltage minus this voltage, right? That is 100 into R4. R4 is basically 45 upon R1 plus R4. R1 is 30 plus 45, that is 75, minus 100 into R5. R5 is 30 upon R2 plus R5, that is 60 plus 30, that is 90, right? So 100, if I take common, this will be 15 into 3, 3 by 5 minus 1 by 3. So this would be 20 into 3 minus 100 by 3. So 60 minus 33.33, that will be some value. 60, that is 180, right? So this is 80 by 3. That is fine. That is my VTH. What about my RTH? RTH is pretty simple. You will have to nullify the sources, right? If I nullify the sources, this will be short circuited, correct? Then what happens? Let's assume this point is A, this point is B, this point is C. So the C point, right, between A and C, R1 and R4 are connected. So R1 and R4 are in parallel. Between B and C, R2 and R5 are connected. So R2 and R5 are in parallel. So if I draw this combination R1 parallel R4, right? R1 parallel with R4. So what is R1 parallel with R4? That will be equals to 30 into R4. R4 would be 45 upon 75, right? 30 into 45 upon 75. So that would be equals to 3 into 3 by 5, 6, 18 ohms, right? 18 ohms. So yeah, this value is 18 ohms. What about R2 parallel with R5? So R2 parallel with R5, that is basically 30 parallel with 60. 30 into 60 upon 90. So this will be basically 20, right? So this value will be 20. And this is my AB point. So basically your RAB is equals to 18 plus 20. That would be equals to 38 ohms. So RAB is equals to 38 ohms. We got that value. So we know our VTH, that is 80 divided by 3. We know our RTH, that is 38. We know our load resistor, that is R3. R3 value is 90. R3 value is 90. Now I hope you can easily calculate the value of the current. That would be 80 divided by 3 upon 38 plus 90. So 80 divided by 3 divided by 38 plus 90. So this comes out to be 0.283. In what direction? Remember, this was my reference direction of current, right? Actually, they even have not told you. Okay, they have given you the direction of current. This is the direction of the current, right? Along this. So basically, this is my A point. This is my B point, right? So this is my A point. This is my B point. So direction of current, whatever they have given, and my calculated direction of current are same. Current is flowing from A to B, right? So your answer would be plus 0.208. Closest would be option B. So option B would be your answer for the question. Bit lengthy, I do agree, but it is very simplified if you use theorems. Let's solve this. So again, a very good question on reciprocity theorem, right? That came in GATE IN 2022. Given circuit A, currents I1 and I2 are shown. Then the current I3 would be what? Okay, and if you see, basically, there is a 48-volt source here. Everything else is same. The circuit is same. What they are doing, they have just given a source here, right? This was previously here. The source is now here. Now remember one thing, right? Always remember one thing. Any resistive network will always be reciprocal. Okay, you will have to, in network, very few things I will tell you to remember, and this is one of those things. Any reciprocal network, sorry, any resistive network that does not contain any dependent sources, that only contains independent sources, any resistive network or any passive network, or like any network, right, that contains RLC and independent sources will always be reciprocal. Now if you ask me, sir, what is reciprocal, what is reciprocity theorem, I will just give you a very brief about it. But if you want to learn more about it, right, you'll have to go and watch our network theory playlist. There is a video of reciprocity theorem. Just search reciprocity theorem PrepFusion, right? You will get the first video. That will be inside the playlist of network theory on our YouTube channel. So you can watch that. I will just give you a very, very little brief. So let's say I have a network here. And let's say this is my port 1. This is my port 2. And I'm providing an excitation here. Right? any excitation, and let's say there is some element, or let's say I'm calculating the current here, right? Excitation I'm providing here, and I'm seeing the effect of current I. Now, if the network is reciprocal, right, then if I swap the excitation and the effect, the values will be same, it will not change. So if the network is reciprocal, then if I provide a voltage of V here, right, although my drawing is not proper here, it's very small actually, let me make it a bit bigger, right, this is the voltage that I'm applying here now, V, and this is the current. Although this network is bigger, but it does not make any difference, both of the networks are same only. So this will be the same current I, right? That is your basic reciprocity theorem. Now there are multiple things to it. If the network is linear here, right, of course the network has to be linear, that is the first thing, network has to be linear, right, it has to be linear. If the network is linear, if I multiply my voltage, let's say, if I don't apply V, I apply 3V, then this current also will become multiplied by 3. Because the network is linear, this will happen. Very small example, like very basic example, right? Let's say I have this resistor and I'm applying a voltage across this resistor, let's say 1 volt of 1 ohm, right? What is the current? Current is 1 amperes. What if I multiply the voltage by 3? What will happen to the current? If I apply 3 volts across the same resistor, then the current also will be multiplied by 3, right? So current also will be multiplied by 3. Because the elements are linear, this linearity property will hold. These are the few things that we use in reciprocity theorem. One more thing, what if I multiply by a minus sign, negative sign? If I multiply a negative sign, nothing changes actually. So basically, what if I change the direction of my source? How? Let's say instead of this, right, what I do? The direction of the source is this, plus minus. So what have you done actually from here to here? You have just technically multiplied a negative sign, right? So let's say if this is V, what have you done from here to here? All you have done is you have swapped the excitation and the effect, and you have multiplied by a negative sign. If you have multiplied by a negative sign, that is minus 1, so your current also will be multiplied by minus 1. So current direction also will change, because current is also getting multiplied by negative sign, right? So current direction also will change now. This will be the direction of the current. That is the only difference. These are the few key things that you can take away from the reciprocity theorem. And trust me, they will ask you question from this point only. These 3 points. One is the reciprocity theorem, another one is the linearity, another one is the basically if I multiply by a negative sign, if I change the direction, that's all. Now they can ask you superposition as well. What is superposition? That if I, let's say, know this current, right, let's say this current was I1, or let's say this current was I2, right, this current is I2, again no problems, this current is I2, no problems, and this current is I1. So when the source V was connected, this current was I1 and this was shorted, right? Now due to this voltage source, right, there will be a current I2 here in this direction. Now if I consider this voltage source as well, this current will not change, this current will still be I1 only, right? But because this voltage source is also connected, so due to superposition, I can apply the principle of superposition, both these currents will be superimposed. What do I mean? If now let's say this voltage source is present there, right, no problems, but this initial voltage source is also present, initial voltage source is also present. If the initial voltage source is also present, what will happen? We can simply apply the principle of superposition, right? We can analyze the circuit one by one. So if I just give you this circuit, let's say nothing is given, right? If I just give you this circuit, this voltage is there, plus minus V, plus minus V, and I want you to identify the current I. Right? How will you compute? How will you compute the current I? We will use superposition. So first, I will nullify this source. If I nullify this source, what is the circuit? It is this circuit, right? Isn't it? Correct? I will nullify this source. That is what we do in superposition because the network is linear. So then my I dash, right? I dash, the first current due to the source V becomes I1. Next, what I will do? I will nullify this source and then I will measure the current here. If I nullify this source, it is this circuit. And what is the current? I2. So your I double dash, remember you have to obviously go with the direction, right? This is your reference direction. So both the currents are actually in the same direction as the reference direction. So both of them will be added. So your I, okay, how did it got deleted? That's pretty weird. Okay, I dash is equals to, so I dash is equals to I1 and your I double dash is equals to I2, right? So your overall current would be I, that is equals to I dash plus I double dash, that is I1 plus I2, right? That is what your overall current is equals to, I dash plus I double dash, right? This is your answer. So that is what you will do. You will use the combination of superposition theorem and reciprocity theorem. That is a very good question, right? Like that is a very good concept that can be asked from this particular chapter. Okay, yeah. So let's come back to our question. That was the explanation. So we have built up a bit of base. Now we will actually try to solve the question. Given the circuit A with currents I1, I2 as shown, the currents I3 in circuit B, right? So what will be the current I3, right? So what we can do is we have to find out this current. We can apply superposition. How to apply superposition? So first I can nullify this source, right? I can compute the current I3 due to this particular source. So that would be equals to, if I draw the circuit, like I'm not drawing the network actually, but okay, let's draw the network. Otherwise you will say, sir, network nahi draw kiya sir, kya kar rahe ho? So 8. Now the other source is nullified, right? Other source is nullified. Okay, my tablet is hanging right now. That is fine. Plus minus 8 volt. So yep. So here, right? Can you tell me what will be the current I3 dash? Okay, I3 dash, because this is only due to the 8 volt source. It's very simple, right? You can just scale this network, multiply the voltage source by half. If I multiply the voltage by half, then the current also will be scaled by half, because the network is linear and reciprocal, of course. So now remember, this is only valid if the network is reciprocal, right? This swapping of the source and the effect, cause and effect, right? This is only valid if the network is reciprocal, right? Otherwise this particular thing is not valid. Okay, so yeah, I will just scale by half. So your I3 dash would be equals to 1 ampere. Very simple, pretty simple, straightforward. Now let's compute for this one. How do I compute for this one, right? Circuit is same. All we are doing is we are short nullifying this particular source right? And now the source is connected here, that is 48 volts, right? So this is a two-step process. Initially, if I have 16 volts connected here, if I swap the 16 volts here, right, and then the current, right, will be swapped here. So what is happening, instead of 48 volts, right, if I use the reciprocal theorem, right, I'm swapping the cause and effect. So due to the 16 volts, the current here was 1 by 3. Now if I connect the 16 volts here, the current here would be 1 by 3. That is what reciprocal theorems tells me. So this will be 16 volts and the current here would be 1 by 3 amperes, and this is my I3 double dash. This is my reference direction. Now if you observe, your I3 double dash and the actual current across the particular branch is opposite. So your I3 double dash actually is equals to minus 1 by 3. That is what your I3 double dash is equals to, right? Minus 1 by 3. So your I3 double dash is minus 1 by 3. Correct? I3 double dash is minus 1 by 3. So if your I3 double dash is minus 1 by 3, that means what? That means your now this is your I3 double dash for 16 volts, right? You will actually have to multiply this by 3. So actually this is not important to us. I3 double dash is not correct, right? This is not correct. Actually, like this is not my I3 double dash. This is nothing. This is something else, right? Because 16 volts is connected. Now I will scale this by 3. So if I scale the voltage by 3, the current also will be scaled by 3. So this will be 1 ampere in this direction. Now it is correct because this is what I have to compute, right? So in this case, your I3 double dash is minus 1. So if your I3 double dash is minus 1, that means your overall I3 would be what? It will be I3 dash plus I3 double dash, that is equals to 0 amperes, right? 0 amperes. So your answer would be 0 amperes for this question. The answer is pretty easy, but the question you need a bit of thinking here, right? So there are a lot of sub tasks, right? Sub steps before actually computing the answer, right? We had initially applied the superposition for this particular case, and then we had applied the reciprocal theorem, and then we had applied the property of linearity. So very good question from theorems, right? Many theorems are getting used in a single question. Very good question. So 0 would be your answer for the question. Let's solve this question. In the given circuit, given, the Thevenin equivalent resistance RTH across the terminals AV would be Thevenin equivalent resistance, right? Pretty simple and pretty straightforward. This would be shorted, right? So nullify the sources, independent sources, current and voltage sources. So current source will be open circuit because I is 0, and voltage source would be short circuit because V is 0. Right, so this is 2 ohms, this is 1 ohms, this is 1 ohms. So all these branches we don't need to consider because they are open due to the current source, and this was short circuited, right? That's why this 1 ohm got short circuited, right? This is short circuited, this 1 volt, so it is gone. So basically this is 2 ohm in series in parallel with 2 ohm, so which is 1 ohm only. So your RTH is 1 ohm. So this was a laddu question, right? Laddu question, because they just want to give you marks, that's all. So RTH would be 1 ohm for this particular question. Let's solve this one, right? In the circuit below, what should be the value of R for maximum power dissipation in R? So you have to be very careful. If they are asking me what is the value of R for maximum power dissipation in R, then it's very simple, right? Then you know your R would be equals to RTH for maximum power dissipation. If they are asking you in some other branch, that means you will have to calculate and think in the question. You cannot blindly use this, right? This can be used only if your load itself is varying and they are asking about the maximum power transfer to the load itself, right? Then only this is valid. This has been taught in the full course as well. So be very careful. In this case, you are lucky. They are asking you the maximum power at the load itself. Then we can simply use this condition. R is equals to RTH, right? This is derived from the equation. You can go and have a look in the theorem. I will not derive it, obviously. So we need to calculate the value of RTH. That's all, right? We have to calculate the value of RTH. So for RTH, this 2 ohm and this 3 ohm will be in parallel, right? Because this voltage source will be shorted. So 2 into 3 upon 5, that is 0.4 into 2, that is 1.2. kilo ohms, right? And then ultimately I will add that in series. So 2.2 kilo ohms, right? So 2.2 kilo ohms would be an answer for the question. Simply RTH is 2.2 kilo ohms. Let's solve the next one. In the circuit below, what is the value of IL to transfer the maximum power to the load? Now this is interesting, right? So all they are asking me, what is the value of IL if maximum power is transferred in the load itself, right? Pretty interesting. So maximum power needs to be transferred in the load. For that, what needs to happen? Basically, the what is the power transfer to the load? If I assume load is a passive load, right? So if current is entering, this will be my positive terminal, right? If it's a load, I will assume it to be passive. So this will be the voltage across the load. So if the power needs to be maximum across the load, that means VL into IL needs to be maximum. So let me compute what is VL actually. So I know this current is 1 amperes, this current is leaving IL. So this current right here would be actually 1 minus IL, right? That is the current that is exiting from this branch. Simply you can apply the, from this node, simply you can apply the KCL at this node. You will be able to calculate 1 minus IL. So it is 1 minus IL. So there will be drop, right? So what will be the voltage VL? VL would be this drop, like, because this polarity is also same as VL and this polarity is also same as VL only. So both will be added, or you can apply KVL as well. Simply you can apply KVL from here to here, right? Anything works, you'll get the same value. So this will be 5 plus 1 minus IL, right? So basically this value is VL. So PL is what? Your power absorbed is what? It is 5 plus 1 minus IL into IL. So this would be 5 into IL minus IL square. So this is my expression for PL and this needs to be maximum. So let me differentiate this with respect to IL, because they are asking me what is the value of IL for maximum power to the load. So IL is a parameter, right? Let me differentiate with respect to IL. I see this will be 6 minus 2IL. This has to be equal to 0. IL is equals to 3 ampere, right? IL is equals to 3 ampere. So yeah, IL is equals to 3 ampere. That is the condition, right, for maximum power transfer, because you get only one value of IL, and if you double differentiate this function, you will see that it is something, it is negative. So that will be the maximum, right? IL equals to 3 ampere would be your answer for the question. Let's solve the next one, right? So for the circuit shown below, the Thevenin voltage VTH is what? So VTH is nothing but the open circuit voltage. If it is the open circuit voltage, there is no current flow, so drop across this is 0. So that this is gone. So VTH is actually across this particular 2 ohm resistor, right? Pretty simple, straightforward. Okay. Now what you can do is you can convert this, right, into a voltage source. You can use source transformation, like voltage, equivalent voltage source and equivalent resistance, right? So its equivalent resistance is 1 ohm and its voltage will be its equivalent current into the shunt resistance, that is 1. That is 1 into 1, that is 1 volt only. This will be 1 ohm and this will be minus plus minus 2. Again I can do the same thing for this one, right? So again I can convert this into a voltage source and a equivalent resistance, right? 2 into 2, I into R, that is 4. Right, and this is my VTH. So now I think it is pretty straightforward and simple for you to compute, right? This is 2 volts. So what is the current? The current would be, why I converted everything into a voltage source, because I have to compute the voltage. It is very difficult to compute the voltage across a current source. That's why I converted everything into voltage sources. So, and be very careful while using this source transformation, because if they are asking current through a particular parameter, right, current through the resistance of this current source, then never use source transformation, never use it, because once you use the source transformation, you will not be able to calculate it. Things will change. I am doing this because I will have to compute a parameter that is outside all this, right? That's why. Be very careful while applying the source transformation. So yeah, so if I see, if I apply a simple KVL, all these resistors are in series. So this will be -1, -2, +4, right? Remember, the plus minus sign is like this, right? Because the voltage source delivers, so that's why it will be plus minus like this. This also will be plus minus like this, because the current source is delivering, right? Right, this is the plus minus. So that's why I have written according to the polarity. Current leaves the positive terminal. Current leaves the positive terminal, right? That's why the positive terminal is here. Got it? Okay. So this will be -2 minus +4, and this will be, let's assume the current direction is like this, I. So I into all the resistors are in series 5, that is equals to 0. So your current actually comes out to be minus. So my assumed direction of current is opposite, right? So it is -1/5. So -1/5, right? Okay. So -1/5 ampere, that is the I. So I actually is in this direction. So what is VTH? VTH would be simply equals to this 2 into I, right? 2 into I plus 4, right? I is negative. Make sure you remember I is negative. -1/5 plus 4. So -0.4 plus 4, that is 3.6 volts, right? So VTH is 3.6 volts. So option C would be a correct answer for the question. Pretty simple, but just be good in calculations and source transformation. Let's solve this one. The network shown below, the maximum power is to be transferred to RL, right? What is the value of RL? Again, if you have to transfer the maximum power across the load itself, then you can simply blindly use RTH equals to RL equals to RTH. You can do that, right? But if you have to compute the maximum power across a different, or like with respect to a different parameter, then you go by the basics. Correct? Here we will not use RL equals to RTH, right? We will not do that. Although that is also a possibility, you can do it actually, but because your like load is not known to you, you will not be able to, because they are asking you IL, right? They are not asking you the resistance value. So that's why you will not be able to do it. So then you will solve using basics. Here blindly use the formula RTH. So I will nullify the independent sources. Dependent sources you cannot nullify, right? I hope you remember, you cannot nullify the dependent sources. So this will be shorted. This will be still there. Minus plus 2, 2, and here I have to compute the RTH. 2 ohm, 3 ohm, 2 ohm, Vx, Vx, right? So yeah. Okay. So if this is Vx, right? These two are in series, right? These two are in series. So what will be this value? Simply voltage divider rule, right? If the current is same, that means their voltage will be proportional to their resistance, right? Current is same. So Vx, let's assume this voltage is some V. Vx by V would be equals to 3/2, proportional to the resistance, because current is same. V is equals to IR. So your V actually is equals to 2/3 of Vx. So what is happening is this is actually 2 by 3 of Vx. And okay, now how do I calculate RTH for a dependent network, right? So what do you do? We technically apply a VDC voltage source, right, which can be 1 volt as well, no problem. We apply a VDC voltage source and we measure the current through it, IDC, and your RTH would be VDC upon IDC. Pretty straightforward. I think we have done this multiple times. Okay, this is interesting. So okay, so what is this current actually? This current, if you notice, the voltage across this resistor is Vx and the resistance value is 3. So current would be Vx by 3. So current through this particular branch is Vx by 3. Current incoming is IDC. So current outgoing in this branch would be IDC minus Vx divided by 3. Now it is pretty straightforward. You can actually, okay, is it pretty straightforward? Yeah, it is pretty straightforward. So what is your VDC equals to? So your VDC, if I apply KVL in the outer loop, right, VDC would be, this is 2 by 3 of Vx and this is Vx. So your VDC, if I apply a KVL in the outer loop, is Vx plus 2 by 3 of Vx, that is equals to 5 by 3 Vx, right? That is what your VDC is equals to. Cool, that's good. So your Vx is equals to 3 by 5 of VDC, right? Now now let us apply KVL in this loop, right? Okay, so if I apply KVL in this loop, what will happen? This voltage is what? Or let us apply KVL in this loop, right? So this will be minus of Vx, right? Minus of Vx plus, now the current direction is this, right? So the drop will be like this. So I am encountering negative sign first. So minus 2 into the current, that is IDC, minus Vx by 3, then plus VDC, right? Because I am encountering positive sign first. So this will be 0. So this will be VDC. Okay, so uh, uh, this would be plus Vx by 3 minus Vx. So minus 2 Vx divided by 3 minus 2 IDC plus VDC equal to 0. So I know what is my Vx. Vx is actually equals to 3 by 5 of VDC. So this will be minus 2 by 5 of VDC plus VDC equals to 0. 3 by 5 of VDC is equals to 2 IDC. So VDC by IDC is actually equals to 10 divided by 3, right? VDC by IDC is actually equals to 10 divided by 3. I'm just thinking, I hope I'm not making any mistakes. uh, this will be 5, 3. Seems like somewhere I have messed up something. Seems like it. plus Vx divided by 3. This will be Vx divided by 3 coming here into 2. This is 2. So this will be 2 by 3 of Vx. That is also fine. So overall 2 by 3 of Vx, that is 5 by 3 of Vx. 5 by 3 of Vx is equals to Vdc. That is fine. So Vx is actually equals to 3 by 5 of Vdc. That is fine. That is fine. Vx minus 2 IDC minus Vx divided by 3 plus Vdc. So I have applied a KVL here, minus Vx plus, hold on a second, this will be minus 2 into IDC minus Vx divided by 3. Plus Vdc equals to 0. So minus, so this will be my, okay, sorry. This is minus, right? This is plus 2 Vx by 3 minus Vx. Okay, plus 2 Vx by 3 minus, so this will be actually Vx by 3 only. Yeah, sorry. This will be minus Vx by 3. Okay, that was a mistake on my VF. So Vx by 3, actually this will be 1 by 5 of Vdc. 1 by 5 of Vdc is actually, this will be 4 by 5 of Vdc. So this will be 2 will be there. So your Vdc upon IDC would be 5 divided by 2, that is 2.5. So this is your RTH and this is your answer, right? So just be careful of the calculations, and you will not be even knowing it because you're doing it in a hurry and it is an NAT type question. So be extra cautious while doing calculations for NAT type questions. Be very cautious, right? Okay, yeah, let's solve doubly question. The Thevenin voltage VTH would be equals to what? Again, very simple, right? Open circuit voltage. So the voltage would be, this is 0 volt, right? Because no current will flow. So I have to compute the voltage here. So current through here is 0, right? So all of the 5 ampere of current will come here, and I know this voltage is 4 volts and this current is 5. So this voltage would be what? 5 into 2, the current across the resistor into the resistance, that is 10 volt. So your VTH is actually equals to 14 volts, right? Straightforward and pretty simple, right? One liner. So yeah, let's solve this one. Like in theorems, very little question came from theorems. Again, interesting question. A benchtop DC power supply acts as an ideal 4 ampere current source. A benchtop DC power supply acts as an ideal 4 ampere current source as long as its terminal voltage is below 10 volt. Right? Its terminal voltage is below 10 volt. Beyond this point, it begins to behave as an ideal 10 volt source. So basically what they are telling me, that the DC power supply acts as a ideal current source as long as its terminal voltage is 10 volts, right? So basically till the point, let me draw the VI characteristics. Till the point the terminal voltage is kept as 10 volt, the current is 4 ampere, it will not change. But the moment beyond this point, it begins to behave as an ideal voltage source for all load currents going down to 0, right? So basically this will be the scenario, right? It behaves as a voltage source. So now the voltage is constant, current can vary. Okay, pretty interesting VI characteristics. It can drop to 0. That's why I have made the current going to 0. When connected to an ideal rheostat, so this particular source is connected, source, I'll just name this as source only, is connected to an ideal rheostat, find the load resistance value at which the maximum power is transferred and the corresponding load voltage and the current. So I want the maximum power to be transferred, right? I want the maximum power to be transferred. If I want the maximum power to be transferred, right, So that is the voltage and the current, right? Basically your power would be what? Voltage into current, because I have just connected a rheostat directly across the source. It will be basically the voltage across the source into the current across the source through the source. I just need to find out the point where this product will be maximum. When it will be maximum? At this point. At this particular point, the multiplication will be maximum, because the moment we reach 4 amperes and 10 volts, right, then this is the maximum point, right? If I go below this, what will happen? Let's say I'm at this point, then the voltage is fixed 10, but the current has reduced, let's say 3.5. So now the power would be 10 into 3.5, that is 35 watts, which is lower. So this point will give you the maximum power, that is 40 watts, right? 4 into 10. So certainly the current and voltage would be 4 amperes and 10 amperes respectively. Now if the current and voltage I know across a rheostat, across a resistance, I certainly know the resistance value. Your resistance value would be nothing but the voltage upon the current, that is 10 upon 4, that is 2.5. So option C would be your answer. Question is pretty easy, but like you will have to pick up the things, right? Few small things you will have to pick up. Very important things, but small things, right? Here your VTH equals to RTH will not work. Your VTH equals to RTH will not work, and they want to frame a question from those particular concepts only, where you will not just use the conventional formulas. VTH equals to, sorry, not VTH, your RL equals to RTH, right? You will not use the conventional things. Yeah, they have asked from those particular points as well. It's not like they have not, but in between they will ask you something like this. So they will throw you a curveball. So be very attentive during the examination hall. So let's solve this question. For the network shown, the equivalent Thevenin voltage and the Thevenin impedance as seen across the terminals AB is what? Right? So Thevenin voltage and the Thevenin impedance as seen across the terminals AB would be what, right? Thevenin voltage and Thevenin impedance. So Thevenin impedance is generally the easier one to find out. So let's compute that. But if I see, like, there are two options that are matching, and anyways the Thevenin voltage is different across all the options. So let me directly compute the Thevenin voltage itself. So Thevenin voltage is nothing but the open circuit voltage. So current again would be 0 amperes. So this voltage I will have to compute, right? VAB. Now this voltage I cannot directly compute here. Why? Because I have a voltage source here, right? So be very careful. Okay, so current here is 0 ampere. So current through this voltage source is also 0 ampere. Here also it is 0 ampere. So the 5 ampere current, it is totally flowing through the 10 ohm resistor. So what is the drop here? That is 50 volts, right? What is I1? I1 would be 5 only. So this value will be 3 into 5, that is 15 volts. So your overall VAB would be 15, because this is also plus, this is also plus, right? Plus 50. So it would be 65 volts, right? So 65 volts would be your answer for the question. Pretty simple, straightforward. You can calculate the RTH as well. That's the homework for you. You can do that, but pretty straightforward. So these many questions came from theorems. Now let's come to the most important topic, that is transient analysis. Let's begin with transient analysis. There are very good questions from transient that have been asked recently, especially from W branch. Generally from EC branch the difficult questions are asked, but from transient we have seen from W branch great questions have been asked. So obviously we'll solve them. First we'll solve again BM, then IN, then EC, then W. So this is the first question. In the circuit given below, Vs is 50 volts, right? This Vs value is 50 volts. Great. Let the circuit reach steady state for SPDT switch at position 1. What does SPDT mean? SPDT basically means single pole double throw. Single pole basically means it has only a single pole, right? And this one single pole can go on this, connect to this side or this side, right? So like this single pole can connect to this side, double throw, right? So here and here. So that is what SPDT means. So I can either throw it here in position 1 or I can either switch the pole to position 2. That's why double throw. Okay, that is what single SPDT means. That's it. Now initially it is at let the circuit reach steady state for the SPDT to be at position 1. So when the switch was at position 1, the circuit was at steady state. Once the switch is switched to position, once the circuit is switched to position 2, the energy dissipated in the resistor would be equals to what? Okay, very interesting question, right? So first of all, I have only a single energy storing element here. So this will be a first order circuit, right? And don't worry, I will discuss about order of the circuit in an upcoming question. Don't worry about that. But here it's very simple. Only one energy storing element. So it's a first order circuit. So when this was at position 1 and they are telling me it has reached steady state. I hope you remember what is the steady state for inductor. Don't just mug up things. Steady state basically means some parameter will not change across the inductor. In case of inductor, the fundamental equation is VL, voltage across the inductor, is L DIL by dt. So at steady state, the current across the inductor will not change. So di dt will be 0. Hence, the inductor will be replaced with short circuit because VL will be equals to 0, right? But this scenario will not always happen depending on the input source and many things, right? In this case, it will happen. So you have to be but careful and be very attentive. In this case, we will replace it with short circuit. So the circuit will be simply like this. I will have a Vs connected, that is 50 volts. And this would be 25 ohms. And the inductor will be replaced with short circuit, right? What will be the current here through the inductor? Current through the inductor would be 50 by 25, that is 2 amps. And we know at steady state what is the energy stored in the inductor. The energy stored in the inductor is half into Li square. Half into L. L is 2. Sorry, L is 0.1. I square. That is 2 square. So this will be equals to 0.2 joules. Now, what happens when I move to position 2? So when I move to position 2, suddenly what will happen? When I move to position 2, now this 50 volt source is not connected. This 50 volt source is open. The circuit can be placed like this. I will have another resistance that is connected, 25 ohms. And then I will have 25 ohms. And we know inductor, I hope you have studied a bit of transient. If you have not, you will have to revise. Inductor does not want to change its state. For inductor, it will be current. For capacitor, it will be voltage, right? It does not want to change this current, right? It wants to keep the same energy. It does not like change. So it will try to keep the same current. It will develop some voltage that will drive the current in the same direction. And this current value is 2 amperes, right? And at steady state, what will happen? Slowly, what will happen? This current will flow through these resistors. Due to this, they will develop some voltage, plus minus like this. And if you see the inductor voltage, right? What the inductor voltage in this particular scenario at, let's say t equal to 0 plus. T equal to 0 plus. What is the voltage at t equal to 0 plus? At t equal to 0 plus, the voltage would be, if you measure your VL, right? If you apply the KVL, this will be 2 amperes into 25, that is 50, and into 50. And if you apply the KVL, simply apply the KVL here, this will come out to be minus 100. So what does minus 100 mean? Minus 100, if I replace here, right? L is positive, VL is negative. So your DIL by dt is negative. So current is reducing, and it makes sense because it is a source free network. Inductor will de-energize through the resistor. So whatever energy the inductor had, all of it will be lost in the resistor, right? Initially, that is the only way. So they are asking me what is the energy dissipated in the resistor, that would be the initial energy across the inductor, right? So the energy dissipated across the resistor would be equals to the E initial across the inductor. That's it. So this will be equals to half L I square, that is basically this value only, right? 0.2 joule. So that is 0.2 joule. So 0.2 joule would be your answer for this question. Question is pretty simple. It's like a 10-second question. Okay. But I am explaining you very slowly so that you can understand each and every point, what is actually happening in the question. Right. So 0.2 joule will be your answer for the question. Let's now move on to the next one. Right. So here we have this RL circuit, and they're asking me that initially we excite it by step current. Sorry, not initially, we excite this RL circuit by step current. Initially at t equal to 0 minus, the current across the inductor is IO by 5. The minimum time taken for the current to inductor reach 99% of its final value. So before starting this, I always want to start with this point. How do I understand the order? Because if it's a first order circuit, you will always say that my response, my transient response, my current response, my voltage response always will be exponential function. There is a mathematical proof. Of course, you are welcome to go to our playlist Transient Analysis. There you can see the total differential equation, mathematical proof. All these things are already there. So feel free to go there. But right now we have exam, so we have to go by the tricks, right? So there is derivation, you can go into that. But to understand whether my circuit, whether my transient response, voltage or current will be exponential, first we'll have to prove that it is a first order circuit. So if, how do I say that the circuit has the order of 1? How do I say it? So order is basically the order of the characteristics equation of the system. Okay, that is a proper definition. If you did not understand it, ignore it. If you did not understand it, ignore it. If you did understand it, put a comment down below and like the video. Okay, but if you did not understand, don't dislike. Okay, don't dislike. So yeah, that will just hamper, so don't do it. So yeah, so first point is, if the energy only has, sorry, if the circuit only has a single energy storing element, then you don't have to worry about anything. Blindly you can say the order of the circuit would be 1. Blindly you can say the order of the circuit will be 1. If so, this or this, if the circuit has multiple energy storing elements but can be simplified to 1, right? Let's say I have multiple energy storing elements like this C1, C2, these are in parallel, but they can be simplified. So these two can be simplified into a single one. They are in series, right? It will be C1 into C2 divided by C1 plus C2, C equivalent, and this will be C1 plus C2, right? They are in parallel. So these are fine. So then also the order will be equals to 1, right? Because effectively you have only one energy storing element, effectively, correct? In this case, no, because we have never studied how can I combine L and C, right? We have never studied this, so not possible here as well. So something like this as well. If I have a circuit like this, R, C, and then R and C, C1, C2, R1, R2. So this is also not, you will not be able to simplify this unless and until all the values are same. R1 is equals to R2, C1 equals to C2. You will not be able to simplify this. So these are not first order circuits. These are certainly first order circuits. Okay. Now, if the order of the circuit is first order, then you can write your voltage or current with respect to this transient equation. How does it come up? Again, I have told you, go into the lectures, you can see derivation is there, right? Okay. So this is the transient equation, where this you will have to remember, and this will help you out a lot. This will help you out a lot. Here, how do I remember it? So you know that at t equals to infinity, the value of the function would be x of infinity, right? So in this equation, if you put t equals to infinity, you will get only x of infinity. Makes sense. At t equal to 0, the value of the function should be x of 0 plus. If I put t equal to 0 here, 0 plus, right? So at t equal to 0 plus, because at t equal to 0, something else can happen, right? We only discussed this transient equation is only valid from t equal to 0 plus to t equals to infinity. Okay, not before that, not before that. Please keep this in mind. Or not before the change of state, if there is a change in the supply or something, right? Not before that. So you will have to keep this in mind. So there are a lot of assumptions here. I'm simplifying a lot of things, right? If you go into the full course, you will realize everything, but 90% of the things will be done here only. So this equation is from 0 plus to infinity unless and until there is a switching in between. Now if you put t equal to 0 plus, what will happen? This will be simply 1. So this will be x of 0 plus minus x of infinity, and x of infinity will be cancelled. So x of 0 plus will be equals to x of 0 plus. So that's how you can validate the transient equation, right? Now, yeah. Okay. So now if the order of the circuit is 1, right, and if the source is DC, most cases the equation of the current or voltage will be this, right? Sometimes the current can be impulsive, depending impulsive or ramp current or voltage depending on the circuit conditions, that we'll have to observe the circuit and then comment. But most of the cases this will be the equation. Sometimes the equation can change depending on the circuit conditions. Okay, so these are the few key points. Now let's come back to our question. At t equal to 0 minus, right, they are telling me that the current across the inductor is IO by 5, and we know inductor does not want to change its current suddenly unless and until something is applied. What is applied? So across this inductor, let's say I had a current of 1 ampere and I connect a voltage source, right? If I connect a voltage source with a resistor, nothing will happen actually here. Nothing will happen, right? It will work as it is, no problems. Like slowly the inductor current will reduce or increase depending on the circuit conditions. Here it will actually it can be anything, like depending on the conditions, depending on the value of R and Vs, right? But what if the inductor had a current flowing of 1 ampere and I connect a current source across it of 2 ampere? Then what will happen? Then inductor will say, I don't want to change my circuit condition, I don't want to change my current, I don't want to change my energy. Current source will say, you will have to change your energy, right? Because I am telling you to force 2 amperes of current, right? I am driving 2 amperes of current and you are telling me that you only want to drive 1 ampere of current. I will not let that happen. It's just like your parents, right? You are saying, I don't want to study, I don't want to study, but they are saying you have to. Like, शर्मा जी का बेटा, उसको इतने मार्क्स आ रहे हैं, तुमको क्यों नहीं आ रहे, राइट? तो तुमको करना पड़ेगा, तुमको पढ़ना पड़ेगा. तो फोर्स कर रहे हो तुमको. अब वो when they force it, then you will have to accept them, right? You will have to agree on them, agree with them. So then you will agree with them, and then suddenly the current will change from 1 ampere to 2 ampere. But the inductor will say, okay, I'm agreeing with you, but I need something special from you, right? So inductor will say that I will change my current from 1 ampere to 2 ampere suddenly in no time, in t equal to like delta t equal to 0, right? In no time, only if you provide me with the impulse voltage. It's just like you say to your parents, only if I get the PS5 console, then only I will study, otherwise I will not study, right? There is something demand. So that is what the inductor demands. Okay, that was the analogy, but actually what happens is suddenly the current is changing from that. So this is the equation, that VL is equals to L DIL by dt, right? So L is some constant number, change in current, right? Changing current, final current minus initial, 2 minus 1 upon delta t. So there is literally no change in time, right? Just at t equal to 0 minus, the current was 1 ampere, at t equal to 0 plus, the current you are saying to be 2 ampere. So there is zero change, like zero difference in time, almost negligible, right? Or this is delta t basically, where delta t is tending to 0, right? And L is multiplied. So basically what is happening, if you write this in terms of signals, this will be L delta of t. Okay, not deriving all the specific values here, but just I'm giving you an intuition what is happening. So this impulse current is flowing through the inductor. So that's what happens, right? That is why it requires an impulse voltage for the current to suddenly change. Similarly, you can do for the capacitor as well. For capacitor, it will require a impulse current, right? Not voltage. So I am not deriving it for capacitor, but something similar will happen. For capacitor, if you connect if you connect a voltage source directly across it, the same things will happen, whatever I have discussed. If you are not able to understand, you will have to go and watch the full video, because this is a revision session. I will not be able to cover everything, but I have just given you enough intuition to so that you can derive these uh, capacitor voltages, like impulsive voltages and stuff, on your own, right? So let's come back to our question. So here in this case, yeah, in this case is interesting. You will say in this case also there will be some impulse voltage developed. No. Why? Because I was directly connecting the current source across the inductor. If I have a resistor, here, right, an inductor had an initial current of 1 milliampere. Previously the current had no other path. Now inductor is saying, don't change my current, I want to keep my current 1 milliampere only. The current source is saying, I want to force 2 amperes, not 1 milliampere, sorry, 1 ampere. I want to force 2 amperes. So resistor will say, no problems, I can take that current, right? So resistor will say, no problems, I will take that current. So this resistor is just like your brother or sister, right? Like senior brother or sister who agrees on everything, right? Agrees everything on on every instruction of their parents, right? So resistor will not deny anything, it will take everything. If it wants, it can change the current from 0 to 1 ampere in just a second, no problem for resistor, right? So that's why resistor is a very simple element. Okay, so that is what is happening. So initially the current across the inductor was initially the current across the inductor was IO by 5, and the current across the current source is IO at t equal to 0 plus, right? Because before t equal to 0 plus, u of t is 0. I hope you know basics of signals. Before t equal to 0 plus, u of t is 0 for t less than 0, and u of t is 1 for t greater than 0. This basic definition you know. So before it was anyways not there, and they have even not discussed about that. They have just told me that at t equal to 0 minus, the current was this, right? So resistor will take the other 4 by 5 IO of current, right? That is what the resistor will take. Cool. So that is what is happening over here. Now at infinity, what will happen? At infinity, again we know that the inductor will reach steady state. There will be no change in the current. If there is no change in the current, it will be totally short circuited. If it is short circuited, the voltage across the resistor is 0. If the voltage across the resistor is 0, that means the current across the resistor is also 0. So basically the circuit will be converted like this. This will be the circuit IO, and this will be the inductor through which the same IO current will flow. Is there any impulsive current voltage happening over here? No. There is no switching. At equal to 0 plus, there is switching, and we have derived the equations, right? So we can safely use the transient equation now. What does the transient equation tell me? That my current across the inductor, I of t, is equals to I of infinity. What is I of infinity? It is I naught plus I of 0 plus. What was I of 0 plus? That will be equals to I of 0 minus, because there is no sudden change in current, that will be IO by 5 minus I of infinity, that is IO of infinity, right? Okay, I forgot to tell you. Yeah, I forgot to tell you how do I calculate the time constant. Time constant is nothing but R equivalent upon L equivalent, right? So in this case, what is the C equivalent? Sorry. So in case of inductive circuits, time constant would be L equivalent upon R equivalent. In case of capacitive circuits, time constant will be R equivalent into C equivalent, right? How do I find out C equivalent here? They're in series, so it is C1 C2 into C1 plus C2. And let's say these two resistors are there, right, connected, R1 R2. So what will happen? Simply whatever current is flowing here, same current is flowing through the R1. So these two resistors are in series. So that's how we write the R equivalent and C equivalent. In this case, it is very simple. We have only a single L and only a single R. So it's very simple, right? So it will be L equivalent upon R equivalent, L upon R. So that will be, so this will be e raised to power minus t upon tau, right? So I'm running out of space. Just give me a bit of space. Yeah. Let me get this equation here. So this will be equals to IO into 1 minus 4 by 5 e raised to power minus t upon tau. Now what is tau? Tau is L by R. L is 10 millihenry and R is 10 kilo. Sorry, 1 millihenry upon 10 kilo, right? Yes. Now this is milli and this is kilo. So ultimately this, like the unit of tau is seconds, right? So milli by kilo, that will be 10 raised to power minus 6, that is micro. So this will be 0.1 microseconds, and I will keep my tau as 0.1 microseconds only. The reason, because my t also I have to compute in microseconds, right? So micro upon micro, this will be unitless, no problems. So everything I will keep in micro only, because the final answer I will have to provide in micro only. Now they are asking me, when will this current reach 99% of its final value? What is final value? IO. So at what time the I of t will be 99% of IO? So 9.99 IO will be equals to IO into 1 minus 4 by 5 e raised to power minus t. At some time t, this will reach the value upon tau, that is 0.1. So very simple to solve using gate calculator. So this, if I solve, this will be 0.99 minus 1 into 5 upon 4 ln into 0.1. So this will be 0.438. So IO would be, sorry, not IO, sorry, time t would be equals to 0.438, and they have asked us to round off to 2 decimal places, microseconds. So this will be 0.44 microseconds. This will be the answer of the question. So pretty simple question actually. Like this much only you will do in the actual exam hall. But to build up the base, you have to learn all these things, and this will be used in every question. For transient, mostly you will never have to touch Laplace. Sometimes you may have to touch Laplace when nothing works, when nothing clicks. You will touch Laplace, but mostly 90% of the questions, 95% of the questions will be solved using basic concepts. So let's go to the next question. So this is the next question. The switch in the following figure has been closed for a long time. Okay, it was closed for a long time and it is opened before t less than 0. It is opened at t equal to 0 seconds. The value of dvc by dt for t equal to 0 plus. Now, first thing that you will observe, is this a first order circuit? No, this is not a first order circuit. This is not an first order circuit, right? Because RC are there, not a first order circuit. But are they asking you some value at t equals to 1 second or 2 seconds? No, they are not asking you that. They are specifically asking you the value at t equal to 0 plus, or if they ask you the value of t equals to infinity. For these two particular values of time, you actually don't need to solve the whole question, right? To get the whole equation of the voltage or the current, you can use your brain. How to use your brain? So if they are asking you the derivative of the capacitor voltage, right, you know this equation, that your IC is equals to C dVc upon dt. So IC, so they are asking me the differentiation of the voltage at equal to 0 plus. So technically, actually they are asking me the current across the capacitor at t equal to 0 plus by C, right? Similarly, if they would have asked you the differentiation of the current of the inductor at t equal to 0 plus, this will be equals to L dIL by dt will be equals to VL of 0 plus. So basically it will be VL of 0 plus by L, or infinity also you can do the same thing, right? So these are few tricks that you must use. So, and they have asked from this particular concept multiple times. So one thing you have to remember, that the current across the capacitor can change instantaneously. The voltage across the inductor can also change instantaneously. What cannot change? The voltage across the capacitor cannot change instantaneously unless and until an impulse signal is applied, or the current across the inductor cannot change instantaneously unless and until a impulse voltage is applied. Sorry, here impulse current, if impulse current is applied, the voltage will change instantaneously. Here impulse voltage has to be applied for the current to be changed instantaneously. These things are very important things that you must keep in your head. So let's start with this. So all you have to do is compute the current at t equal to 0 plus, right? So for getting the current at t equal to 0 plus, we will have to see what has been happening at t equal to 0 minus, right? At t equal to 0 minus, this switch was closed for a long time. So if it was closed for a long time, the circuit will reach steady state. So here I have my inductor, here I have my resistor, and this is my capacitor, and this switch was closed for a long time. So if the circuit is in steady state, this inductor will be replaced with short circuit, this capacitor will be replaced with open circuit, right? They are in steady state. Why we replace it with short circuit and open circuit? I have discussed this, right? dvc by dt will be 0, dil by dt will be 0. That is the reason. Okay, basically your IC will be 0 and your VL will be 0. So what is the resistance value? It is 4 ohm, right? And this is open, so no current is flowing. So ultimately these two resistors are in series. This is also 4 ohms only, right? So what is the current through the inductor at t equals to 0 minus, right? Before the switch was open, because it was at steady state. So IL of 0 minus would be equals to 12 upon 8, that is 3 by 2, that is 1.5 amperes. Okay, that is 0 minus, right? Now your this is the case. Okay, now what is happening and what is the voltage across the capacitor? The voltage across the capacitor, right, will be simply 6 volt, because simple voltage division rule, it will be 6 volts at equal to 0 minus. And these things will not change at equal to 0 plus, right? These things will not change unless and until some impulsive voltage or currents are applied respectively. So if I draw the circuit, at t equal to 0 minus, so this will be open circuited, the switch will be open circuited, right? So 0 plus, switch will be open circuited. This was at t equal to 0 minus, at t equal to 0 plus, and I will have the capacitor whose voltage would be still same, that is 6 volt. It will not change instantaneously. The current also will not change instantaneously. Now these two things will fight with each other. The inductor will say, I want to drive 1.5 amperes of current. Will the capacitor deny it, or will the capacitor have a problem with that? No, because the current across the capacitor was 0 and the current suddenly wants to become 1.5. Will it have any problems? No, current can change suddenly through the capacitor. Now current is 1.5 volts. If this current is 1.5 amperes, what is the voltage drop? This drop would be 6 volts, correct? And in this voltage was 0 and here this is 12 volt. So what is the voltage across the inductor now? So if I apply KVL, minus 12 plus 6 minus VL equal to 0, right? So equal plus 6, right? Plus 6. Okay. Hold on a second. minus 12, this current is flowing in the same direction, 6, this will be same only, this voltage will not change, and still the voltage across the inductor comes out to be 0 only. So we don't have technically a problem. The voltage is 0, it can be 1 as well, it can be 2 as well, no problems with that, right? So voltage can change instantaneously, there is no problem for the inductor. Like, at least all you need to care about is, as long as this current is not impulsive for the capacitor, as long as this voltage is not impulsive for the inductor, the current will not change for the inductor instantaneously, or the voltage will not change across the capacitor instantaneously. These things go hand in hand, right? Please replay that particular statement, you will understand it. Okay, so yeah, so the current through the capacitor at t equal to 0 plus is actually 1.5 amperes. This is my concern, right? This is equals to 1.5, and I have to compute dvc by dt, that will be 1.5 by c, right? That will be the differentiation of the voltage across the capacitor at t equals to 0.1. So 1.5 by c, right? C is 1.1 farad, so this will be 15 volt per second. This will be your answer for the question. Let's move on to the next one. In the circuit shown, the switch is opened at t equal to 0 seconds, right? Again, only a single energy storing element, so this will be a first order circuit, and we are opening the switch at t equal to 0 plus the current I of t at t equals to 2 milliseconds would be equals to what? The current I of t at t equals to 2 milliseconds would be equals to what? Now this is a first order circuit, right? We can simply use our transient equation, right? So before t equals to 0, the switch was closed. Now if you see, if the switch was closed, the circuit was in steady state, right? So the current source gets a short circuit path. If the current source gets a short circuit path, I will not even care what is there in the right hand side, right? All of the current will flow through the short circuit path until and unless the right hand side is also short circuit. Until and unless the right hand side is also short circuit, other than that I will not care about it, right? Okay, then we will have to think about it. So t equal to 0 minus, the current was 0 across the inductor. At t equal to 0 plus, again the current can be 0. Once the switch will be opened, what will happen? The inductor current will be 0, it will not change its current instantaneously, so it will behave as open circuit, right? If it behaves as open circuit, because current does not want to change instantaneously, so is there a problem? Will the current source say, no, you will have to take some current? No, because I have a resistive path in parallel, so all of this current 10 milliampere will flow through the parallel path. So no impulsive voltages are getting applied, no sudden changes in current, we are safe. So we can safely use our transient equation, right? But this is a first order circuit, I will safely use my transient equation. Transient equation tells me what is the current at, so what are they asking? They are asking me the current I of t. I of t is the current across the resistor. So we can safely use a transient equation anywhere, any element you use at any element, it will always work. So if I want to use a resistor, I will write the current across the resistor at t equals to 0 plus. So first, what did I check? Is this a first order circuit? Yes. Are there any sudden changes in voltage or current, right? Especially current for inductor and voltage for capacitor. Are there any impulse voltages for inductor, impulse current for capacitor? Check. So these are the checks, right? First you will check the order of the circuit, order. Then you will check that sudden change, order of circuit, sudden change in there are two things, right? In voltage, in current. So voltage would be for capacitor, right? Because capacitor does not like to suddenly change its voltage, and current would be for the inductor. Now these two conditions are checked, right? If it is no, if there is no sudden change in voltage or current, right? If no, then use the transient equation. Then we can safely use our transient equation. I know there is a lot of confusion. I have tried to clear out each and every confusion in this single video, and trust me, this will help you out a lot. If it changes suddenly, then you will have to analyze the circuit. So I of t, again it will be equals to I of infinity across this resistor. What is the value of the current at t equals to infinity? At t equals to infinity, the inductor will behave as short circuit. There will be no changes in the current, so it will behave as short circuit. So the circuit will be something like this, right? So simply I can replace this with short circuit here. Okay, you cannot see. Simply I can replace this part with short circuit here, right? Inductor will be short circuited. So so this will be 40 into 40 plus 40, right? This side is 40 plus 40 in parallel with 120. So for 80 into 120 upon 200. So this would be 4 into 12, that is 48, right? 48 ohms. Okay, and then 48 ohms. Am I correct here? Yeah, 48 ohms. This side is 48 ohms. Okay, actually, right, we don't even need to worry about this. So what is happening? This is a current source, right? And this path is actually open circuited, right? Because we're opening the switch at t equals to 0 plus. So these two series resistors are actually redundant. They are just there to scare you, because whatever the current that will go out, right, from here, let's say I current, same current will come from here, right? So this does not matter if I place here 1 kilo ohm, 1000 kilo ohm, 1 mega ohm, because this is an ideal current source. These two resistance will not matter, right? So ultimately what is happening, this I current is getting divided in this two parallel resistances, right, whose combination here is, this is 80, this combination, right, this and this, okay, sorry, how did it got deleted, this and this and this, right? So these two are uh, my resistance. So overall I can use my CDR. So I'm just doing this in a hurry because, like, I hope you know these basic things, because basics already has been covered in the first chapter. So 80, so it will be opposite resistance, sorry, it will be the resistance across here, right, current. So it will be the opposite resistance, that is 80 upon the overall resistance, that is 120 plus 80, right, that is 200. I am simply using the CDR, current division rule, right? This is 120 ohm, this overall combination is 80 ohms, right, into the overall input current, that is 10 milliamperes. So this would be 10 will go there, 10 will go there. So this will come out to be 4 milliamperes. Okay. So the initial current is 4 milliamperes. Initial current is 4 milliamperes. What about the, sorry, the final current is 4 milliamperes. What about the initial current? So initially, right, at, so this is the final current 4 plus the initial current. Initial current is when this inductor will behave as a open circuit. If this inductor behaves as an open circuit, all of this 10 milliamperes of current will flow through the this path, right? Because this inductor will behave as open circuit, because at t equal to 0 minus there was no current through it, right? It was 0 amperes, because all of the current was flowing through the left hand side. So that's why all of this 10 milliamperes of current will flow through the resistor. So I will directly write here 10 minus I of infinity, that is 4, into e raised to power minus t upon tau. Now you will have to compute the tau. So to compute the tau, again we will nullify the independent sources. So our current source will be nullified. We'll have a resistor over here, that is 120, sorry, this will be 50, this will be 100, ohm, this will be 40, this will be 40, right? And I'm measuring the R equivalent through the inductor terminal, right? We have to measure the R equivalent through the inductor terminals, okay, through the inductor terminals, inductor points. So of course this is open circuit, right? So no current will flow through here. It is simply the series combination of these resistances, right? So R equivalent through these 2 points will be the series combination, that is 200 ohms. So my R equivalent is 200 ohms, pretty simple and straightforward. What about my L equivalent? I have only a single inductor, that is 0.2, so my L equivalent is 0.2, right? And they have asked me time in 2 milliseconds, right, in milliseconds. So my tau also I will try to write in milliseconds only. So this will be tau will be equals to L by R. L is 0.2, R is 200, so this will be 0.1 by 100, so 1 milliseconds. So tau is 1 millisecond, right? Tau is 1 millisecond. So your I of t will be 4 plus 6 e raised to power minus. Now they are asking me the current at t equal to 2. So this will be 2 upon 1 millisecond. Both are in milli only, so no problems with that. So let me compute this value. So e raised to power minus 2 into 6 is to minus 2 into 6 plus 4, that is 4.81. 4.81 amperes will be your answer for the question. Let's now move on to the next one. So we are starting with EC now. Again, whenever you see that we have RLC, mostly they're asking the differentiation at t equal to 0 plus or t equal to infinity. Mostly this will be the case. Sometimes they might ask you the whole few other things as well. For that you will need the help of Laplace, okay, which we will obviously discuss. Don't worry about it. We'll try to cover each and every particular topic, right? So the switch in the circuit in the figure is in position P, right, for a long time. Now it is moved to Q at t equal to 0. Now they are asking me what is the voltage, derivative of the voltage at t equal to 0 plus. Again the same thing, it will be simply IC of 0 plus by C, right? I have to check whether there is some impulsive current or not. Mostly it will not be the case, we'll see. So when it was at position P, what was the steady state condition? This inductor was replaced with short circuited, right, because it was at steady state. This capacitor was replaced with open circuit, right, because like we are assuming it to be in steady state only. So and I have told you why it is in steady state, like previously, like why it is open circuit in steady state, right? If like there can be a certain case, I know a few students might have doubt that what if the current, right, is oscillatory in nature? What if the current is in oscillations? So there can be damped frequency of oscillation as well. That is a possibility, I do agree. But mostly in these kind of questions, right, your current will never be oscillatory. It will reach a steady state and it will be oscillatory. I will show you when it will be oscillatory. Don't worry. There is a question as well. I will tell you when it will be oscillatory. But mostly there will be oscillations. You are correct. There will be oscillations. So this is a second order circuit. For the students who have studied control systems in time response, you know the unit step response of a standard second order system is like this. There will be oscillations due to this R and L. You are correct. But ultimately, if you remember the graph, right, of the response, it reaches steady state at t goes to infinity. So there will be oscillations, but it will certainly reach steady state, right? I hope you remember the graph. So this graph again will be used in a question, okay, later, don't worry. So what is IC of 0 plus? For that I have to check the conditions here. So 0, what is happening at 0 minus? So this is the circuit at 0 minus, right? So we will totally remove the cap and remove the inductor, like short the inductor, right? So what is the current across the inductor at t equal to 0 plus 0 minus, sorry. So t equal to 0 minus, this is in parallel and this 20 volt is connected across these two resistors in series, right? So this will be 20 upon 10 plus 10, that is 20 kilo ohm, that is 1 milliampere. So IL of 0 minus is 1 milliampere. What about VC of 0 minus? So VC of 0 minus obviously will be totally the drop across this 10 kilo ohm, that is simply 10 volts, right? You can apply the voltage division rule, that will be 10 volts. Now these things should not change instantaneously until and unless something impulsive is getting applied, right? So let me now move the switch to position Q. If I now move the switch to position Q, what is happening? This technically becomes a charge free network. So suddenly there is a resistor here, right? So voltage will not change suddenly because all of the voltage drop, whatever was there 10 volt, it will come across the resistor, no problem. So what will be the current? through this resistor now, because the voltage, right, will not change instantaneously across the capacitor. The current will be 10 by 5 because all of this voltage is getting applied across this resistor. So 2 milliamperes will be the current across the resistor, right? And inductor again will not change its current instantaneously unless and until something impulsive is getting applied, right? And it is not getting applied because the voltage here is a finite value, so it is not impulsive. So this current will not change. This will be 1 milliampere, right? So the current through the capacitor actually will be, if I apply the KCL here, 2 plus 1 milliampere, that is 3 milliampere, right? That is 3 milliampere, right? So the current will be 3 milliampere. Now it is outgoing from the capacitor, right? So capacitor is discharging. It is outgoing from the, not capacitor, sorry, outgoing from the positive terminal. Outgoing from the positive terminal, because this was the initial voltage direction, right? Plus minus 10. This was the direction of the capacitor voltage. They have even provided you the direction. Okay, and this was my reference direction, that is 10 volt. No problem. Now it is discharging. Okay, so you will say that it is IC upon C. So this will be 3 upon C is 1 milli. So 3 milli upon 1 milli, that is 3 volt per second, and you will mark the option B and you will be wrong. So be very careful of the sign as well here. Your capacitor is discharging. How do I represent discharging? The voltage will reduce, right? Because current is leaving the positive terminal, energy across the capacitor is reducing, so voltage will reduce. So your IC is equals to IC equals to C dVc by dt. So your voltage is reducing, right? How do I show reduction? You say that your IC is negative, right? Basically your dVc by dt is negative, then only I can say your voltage is reducing, because here it is certainly discharging. It is a source free network, it will certainly discharge. So if it is reducing, or if the current is leaving the positive terminal, right, that means the voltage is reducing, it is discharging. So your dVc by dt will be negative, so it will be minus 3 volt per second, not plus 3 volt per second. Just be mindful of that thing, right? If the current would have entered the positive terminal, that means the capacitor is energizing, that means the voltage is increasing, right? More energy is getting in, voltage is increasing, hence it will be plus 3 volt by second. But in this case, it is leaving the positive terminal, energy is reducing, so it will be minus 3 volt per second. So option C will be the answer for this question. Let's now solve the next question. In the circuit shown in the figure, the switch is closed at t equal to 0. Okay, so at t equal to 0, the switch is closed. Initially, the capacitor voltage before t equal to 0 was minus 5 volt, right? It is shown as minus 5 volt. The time after which the voltage across the capacitor becomes 0, right? When will the capacitor voltage become 0 basically? Okay, that's pretty interesting. When will it become 0? Again, only single energy storing element, so order will be 1. Certainly order will be 1. Now let us see, will there be any transient currents or voltages at t equal to 0 plus, at t equal to 0, right? After the switching, basically here, right, this sudden change during switching, we'll have to check only during switching, right? Then we are safe. So here, this will be interesting, right? So before t equal to 0, right, what is happening before t equal to 0? The circuit is something like this. So there is no connection here, right? This is open circuit, and this capacitor voltage is always minus 5, so this will always remain at minus 5. There is no connection, there is no current through the capacitor, so no problems, right? And here what will be the current? So this will be VR by 500, right? So all this does not matter because here there is no energy storing element, so we don't have to worry about this, right? We don't have to worry about anything here, right? Because currents and voltages can change instantaneously here, because all these are resistive components and sources, no problems. So all we are concerned about is the voltage across the capacitor at equal to 0 minus, which is minus 5 volt. That is already given, not minus 5 amperes, minus 5 volts. Now let me close the switch. if I close the switch, interesting will happen. So minus 5 volt is across the capacitor. So across this resistor is minus 5 volt. So through this, what will be the current? Current will be like this, isn't it? Because it is minus 5 volt, right? Minus 5 volt would be like this, plus minus 5, right? It is negative. So I will have to flip the sign. So this will be 5 by 250, that is 1 by 50, right? 1 by 50 is nothing but, okay, let me keep it 1 by 50 only. So 1 by 50 of amperes, 1 by 50 amperes of current is flowing like this. From here it is VR by 500. From here, how much current is flowing? I know the voltage across this resistor. I know the resistance of this resistor. So from here, the current that is flowing is VR by 250, right? Okay. So we can apply a bit of KVL here, right? If I apply a bit of KVL here, like this voltage is, so I know you will be confused with sign. So let me write this plus minus only, and then I will replace my VC with minus 5. Don't worry about it, right? So I will start with minus 5 plus VR plus VC of 0 plus. I'm writing the KVL at t equal to 0, right? I'm completing a whole loop. Now VC itself is minus 5. VC itself is minus 5. The sign of VC is given. I'm just choosing the first sign, and VC itself is minus 5. So your VR would be what? VR would be minus 10. Okay, very careful. VC itself is minus 5. So VR is actually minus 10. It is opposite. So current actually will flow in this direction. It is opposite, right? So this will be minus 10, that is 10 by 25, that is 1 by 25. And this current will be, again, this will be opposite, right? Because VR itself is negative. So your actual current is flowing in this direction, that is 10 by 50, that is 1 by 50. So 1 by 50 current is flowing from here, 1 by 50 current is flowing from here. So according to KCL, the sum should be valid. So actually, if I apply the KCL through here, 0 amperes of current is flowing, right? So I'm safe there. I don't have to worry about that. So current is not changing instantaneously, or sorry, current is some finite value. It is not impulsive. So we don't have to worry about it, right? So now what I will do is I will apply the I will apply the transient equation. I will apply the transient equation. So at t equals to infinity, what will happen? At t equals to infinity, right? If I copy the circuit, the capacitor will behave as open circuit, right? So there will be no connection because it will be steady state, and the current across the capacitor will be 0. It will be some constant value. The voltage will be some constant value, right? So if it is open circuit, then what will happen is that then I can see the parameters. Again, I can apply a KVL in this loop, right? So if I apply KVL in this loop, so this current is VR by 500, right? And this current is again what? VR by 250, and this current is outgoing VR by 500. So this current also will outgo VR by 500 only if I want to satisfy the KCL, because there is no current through here, right? So this current is VR by 500. So what will be the drop? The drop would be VR by 2 across this resistor. The drop would be VR by 2, right? Now apply the simple KVL. It will be minus 5 plus VR by 2. That would be equals to 0. So 3 VR by 2 would be equals to 5. Ten by 3. That is my VR voltage, 10 by 3, right? We got our VR voltage. If I know my VR voltage, I can certainly find out the voltage across the capacitor, because remember the switch is closed. Although the switch is closed, right, the capacitor is open circuited. The capacitor is open circuited, but switch is closed, right? Sorry, I draw the circuit in a wrong manner. Switch is closed, right, but the capacitor is open circuit. So the voltage across the capacitor will be the voltage across the resistor of 250 ohms, that is VR by 2. So your voltage at infinity, right, VC of infinity, this is the circuit at t equals to infinity. This is the circuit that I have drawn here at t equals to 0 plus, and at t equal to 0 minus, we don't have to worry, right, because all the elements were resistive on the left hand side of the circuit, so no need to worry about that. So at infinity, your Vc of infinity is equals to basically 5 by 3 because it is half, right. So we got our Vc of infinity, we got our Vc of 0 plus, that will be equals to Vc of 0 minus only, right, because there is no impulsive currents, so it will be minus 5. So now I can safely write my transient equation. It will be Vc of t will be equals to Vc of infinity, that is 5 by 3, plus Vc of 0 plus, that is minus 5. Like 0 plus is there, only this can be this, right, whatever I have written here, this will be the basically or 0 plus or switching instant. Whatever is the switching instant, according to that, the time will change, right? Minus 5. And then minus of Vc of infinity, that is again 5 by 3 into e raised to power minus t upon tau. So what is tau? Tau is R into C, right? Because I have a RC network. So what is the R? What is the R equivalent here? How do I find out the R equivalent, right? To find out the R equivalent, this will be pretty interesting. So you will have to find out the R equivalent across the capacitor, right? That's how we find out the R equivalent. If I forgot to tell you, the R equivalent will be found out across either the capacitor or the inductor, right? So this will be found out across R, sorry, inductor or capacitor, right? Across L equivalent and C equivalent, the R equivalent. It is nothing but the RTH, and I know you know how to calculate the RTH. I hope you know how to calculate the RTH. So so this will be basically, I will nullify the sources, nullify the independent sources. Of course, I cannot nullify the dependent ones. So this will be 250. This will be VR. This will be 250, and here I will compute the R equivalent, right? So so this voltage is VR, so this voltage is also VR. So through here as well, the current would be VR by 250, right? Both these voltages are VR only. So if I'm applying a voltage, let's say V, and I will measure the current I, and my equivalent resistance will be V upon I, right? So I can safely say that my V is equals to minus of VR, right? It is just opposite. So this is VR by 250, and this current is also here VR by 250, that is incoming here. This current is outgoing. So if I apply a KCL at this node, right? So this will be incoming current, that is VR by 250 plus VR by 250 plus I equals to the outgoing current, that is VR by 500, right? So okay, so my I would be equals to what? I would be equals to, this will be VR minus, this is to 4 VR by 500 minus 3 VR by 500. So that is what my current is equals to. right? So yeah, that is what my current is equals to. Now yeah, we can simply take the ratio of V upon I, that is minus of VR upon minus 3 VR by 500, that is 500 by 3. That is the R equivalent, and L C equivalent is very easy. It is 0.6 microfarad. So your tau, right, is 0.6 micro into 500 by 3. Right. I want to compute the tau in milli because answer also has asked me in milliseconds for time. So I will compute the tau in milliseconds. Right. So this will be 0.6 into 0.5 divided by 3. That is my tau. So 0.3 divided by 3, that is nothing but 0.1 milliseconds. So I will put that tau in the equation. So when the voltage will reach 0, right? When the Vc will reach 0, so basically I will put here in this equation Vc of t equal to 0 equals to 5 by 3. Now this will be minus 15 minus 20. So minus 20 by 3 e raised to minus t upon tau. So tau is 0.1 basically. So so this will be 4 1 by 4, so 0.25 ln into 0.1. So your answer would be 0.13 9 milliseconds, because they have asked us to round off to 3 decimal places. So 0.139 milliseconds would be your answer for the question, right? The circuit in the figure contains a current source driving a load having the inductor and a resistor in series with a shunt capacitor across the load. The ammeter, okay, this question is pretty interesting because here we'll use the concept of uh, sudden changes in the current, but we'll use that concept. So let's see this question. So they're telling me that initially the switch was open, right? Consists with this shunt capacitor. The ammeter is assumed to have zero resistance. The switch is closed at time equal to 0. So before that it was open, right? So everything was in steady state. There was no currents, no voltages. Everything was 0, right? Before closing the switch. Initially the switch is open, capacitor is discharged, and the ammeter reads 0 ampere. So there is no current. So the voltmeter also will be 0 volts only. There is no current, no change in current. So sorry, the inductor voltage also will be 0. Okay. Now what happens after the switch is closed? The ammeter current keeps on fluctuating for some time, still till it settles to a final value. The maximum ammeter reading that one will observe after the switch is closed will be. So trust me, if you have learned, like if you are learning from some other institute, right? So they will say that this particular question most of the educators will avoid. Like there is nothing. This question is pretty simple. But what will happen? The problem is educators will be able to solve it, but they will say, uh, if someone is teaching network, they will say this is a question from control system, so this will be taught to you in control. And if someone is teaching you control, and that educator will say this is from network, so that will be taught to you in network. So question is pretty simple, but it will not be discussed, right? That's the problem. But at PrepFusion, that problem is not there because both the educators know everything, so we can teach everything. So yeah, so here if you see what will happen, so for this you will need a bit of basic knowledge of step response of a second order circuit. So you will have to study the time response chapter from control systems. If you have not, you must go and study that. If you don't understand that, then I will not be able to, like, I will not you will not be able to understand my discussion over here. So what happens if I see, once I close the switch, this circuit is nothing but a second order circuit. This circuit is nothing but a second order circuit, right? Now if this circuit is second order circuit, right, what we need to find out is the response of the circuit, right, will be something like this. So if they are talking about the uh, ammeter reading, so if they are talking about the ammeter reading, they are talking about the inductor current, right. So initially, right, as soon as the switch will be closed, the capacitor has 0 voltage, so it will behave as short circuit. So if the capacitor behaves as short circuit, what will happen? All the current will flow through the capacitor, none of the current will flow through the inductor. So at t equal to 0 plus, the current across the inductor is 0, and that is fine because inductor does not want to change its current instantaneously. Also, the current across the capacitor is also constant. Current can change across the capacitor instantaneously, but voltage is 0, no problems. So both the cases, no problems, right? That is not a problem, right? So it starts from 0, and then slowly what happens? Slowly, as the capacitor current is flowing into the positive terminal, right, the capacitor will energize. If the capacitor energizes, this voltage will increase. If this voltage increases, there will be some current that will flow through the resistor as well, that will again energize the inductor. Why? Because this voltage will be positive, and if VL is positive, DIL by dt will be positive, so the current will increase. So inductor also will slowly energize, hence the current also will increase. Now this I'm telling you intuitively, like there is Laplace, you can do it with Laplace as well, no problems, right? And this will increase, and because it's a step input, right, because I'm connecting the switch at t equal to 0, before that it was not there. So for a step input, the response is somewhat like this. Okay, there will be some damping. What is damping? When will we reach steady state? All these things has been taught to you in control systems. So unfortunately, you will have to go there and learn about these terms, right? So this will reach steady state at 4 tau basically, and tau is basically 1 by zeta omega n. All these things has been taught to you, so I will not be able to say what is zeta, what is omega n. Zeta is the damping ratio, omega n is the natural damping frequency. I will not be able to discuss here, unfortunately, right? So what they are asking me, they are asking me what is the maximum ammeter reading. What is the maximum ammeter reading? Maximum ammeter reading would be when I reach the first peak, right? First peak. And again, there is a formula for this. Unfortunately, you will have to remember it, right? I have taught this very well. You can go to the R-PYQ video, the time response part. That is the first video, right? First video of R-PYQ where I have discussed time response. You can go to that and just watch it. Go to that first video, first R-PYQ video of control system. There I have taught in a very good manner what is time response, what is the step response, right? How to derive each and every parameter, how to remember this. So this actually is called the maximum peak overshoot. That is actually equals to e raised to power a into k. Sorry, the maximum peak overshoot is equals to e raised to power minus pi cot theta, where theta is basically your cos theta is basically zeta, right? These things I have taught there, how to remember everything there, right? Not be able to teach you here, unfortunately. So this is my maximum percentage peak overshoot, right? Now if I want to write in absolute terms, it is actually equals to a into k into 1 plus e raised to power minus pi cot theta, basically, where a into k is the steady state value. A is the value of the step, amplitude of the step, and k is the DC gain of the transfer function, right? So again, if you don't understand anything what I'm saying, you will have to go there and watch the video, right? R-PYQ video. So in this case, a value is 1 only, right? 1 ampere. What about the transfer function? What about the transfer function, right? What is the DC gain of the transfer function, right? So for that, actually, we'll have to calculate, right? Just little bit of Laplace I will use, just a little bit, okay, not much, just a little bit. So I will have to write the current, right? Ammeter current, that will be equals to what? So if I draw the Laplace equivalent, this will be 1 by Cs, this will be Ls, this will be R, right? And there is this current source, so I can replace, like this I am not teaching you, right? This will come to be 1 by S, right? I am not teaching you these things, but my expectation is you already know all this, right? You already know all this. Okay, so this is actually my A by S, right? Input signal. So A is Like I'm assuming the step to be A, and A value is one that I know. A value is one that I know, right? But let's just assume it is A by S, right? So basically I'm assuming the current here to be AUT. This is just like a step current, right? A into UT, where A is 1, right? Should not be a problem to you, but I'm assuming it to be A to properly tell you what is happening, right? So we have to measure this current IA of S, right? So what is IA of S? Upon the input, right? Okay, so this is my II, the input current, II of S. So what is the IA of S in terms of the IIF, input current, right? Input current Laplace. So although I'm not writing you here the A by S, but you know this is in Laplace domain, this will be II of S, the input current in Laplace transform. So this will be equals to this will be equals to, I can apply the current division rule, II of S into 1 by C, opposite impedance upon the total sum of the impedance 1 by Cs plus R plus Ls, right? So your transfer function, right, Ia of S upon I of S, this is the transfer function, right, here, and this K is the DC gain of the transfer function, that's it. So I'm concerned about K, that's why I'm doing all this. So Ia of S upon Ia of S would be equals to 1 divided by 1 plus RCS plus S square LC. So now you find out the DC gain, right? So your DC gain would be S equal to 0. So your K would be equals to, this will be equals to K when my S is 0, right? DC gain. So if you're not understanding anything, you will have to revise control system. You will have to revise control system. So S equal to 0, this will be equals to 1 divided by 1 only. So DC gain is 1. So they will, mostly they will give you simple things only. But if they want to frame a very good question, they will change the value of DC gain. They will change the value of the unit step. They will change, make it 2, right? Then your answer will change. That's all. So K is 1, A is 1. So your answer is actually very simple. It is 1 plus e raised to power minus pi cot theta. How do I find out cot theta? I have to find out theta, right? That is cos of theta equals to zeta. How do I find out zeta? Zeta would be this. So let me convert this into proper characteristics equation format. That will be s square plus s into r by l plus 1 by lc equal to 0. Right. So this will be how to find out the zeta. So if you don't understand anything here, right, because you have not studied the subject, right, you will have to go and study. So that's what I'm telling you. All questions would not be like that. If you have never studied this particular topic and you will be able to solve it, it's not like that, right? You will have to study it at some point. So here your omega n would be equals to 1 by root LC, right? This is omega n square, because our standard equation is s square plus 2 zeta omega n s plus omega n square, that is equals to 0. So your zeta would be, if I compare the equations, this will be r by so 2 zeta into omega, that is 1 by root LC, that is equals to r by l. So zeta is equals to c by l by 2. So that is my zeta. So zeta is this value, right? So yeah, zeta is this. So what is my r, l and c? So we'll have to put the values. So r is actually how much? R is 5 kilo, 5k, okay, upon to c is 100 pico, and l is 10 milli. So this will be 10 into 10 raised to the power minus 15. So I can write 10 into 10 raised to the power minus 14. So 2.5 into 10 cube into 10 raised to the power minus 7. Right. So this will be a very small value actually. How is this so small? Sorry. This will be 10 raised to the power minus 9, right? This will be 10 raised to the power minus 9, 10 raised to the power minus 8, 10 raised to the power minus 4 actually. This will be 10 raised to the power minus 4. So this will be 0.25. This is my zeta. So what will be my theta? Theta will be cos inverse of 0.225. Remember to do it in whatever proper units, right? So 0.25 cos inverse, that is your theta is coming out to be 75.52 degrees. You will have to write the cot of this, right? So cot would be take the tan and then take the inverse. This would be cot theta would be equals to 0.2582, and you'll have to multiply this by pi and minus 1, right? So min into pi and negative 1 and take the exponential of this. So this will be 0.44, right? 0.44. So 1 plus e raised to the power minus pi cot theta would be equals to 1 plus 0.44444 into 1, aka is 1, so it will be 1.44. So 1.44 ampere will be your answer. This question is pretty good, like very good question actually, because a lot of concepts are getting asked. Control system, even in control system, lot of things are getting asked here, right? It's not a single concept. So this would have been even better if they would have made the d-secant to be not equal to 1. Then this question would have been very difficult, and very few people in the actual exam hall would be able to solve these kind of questions, because you will need good intuition as well, because you will not be able to solve with just Laplace, right? You will need good intuition to understand what is actually happening in the question. So 1.44 will be answer of the question. Let's now solve this question, right? This is the next question. In the circuit given below, the switch S was kept open for sufficiently long time. The switch is closed at t equal to 0. The time constant of the circuit is. So they're simply asking you the time constant. Don't worry about anything, right? Don't worry about initial final conditions. Don't worry about that, right? So if at t equal to 0, I'm closing the switch, right? So they're asking me the time constant after t equal to 0. So I will draw the circuit after t equal to 0 only. I will consider the circuit after t equal to 0 only. I will not consider before t equal to 0. And they're asking me to find out the time constant. So I have only a single element, single energy storing element. So no worries. All I need to do is calculate the R equivalent. For calculating R equivalent, I will nullify the independent energy sources, right? That is 5 ampere, independent sources. So this 5 ampere will be gone, open circuited. This will be 2, this will be open. This switch is also closed. So this is 4 and this is also 4, right? So 4 and 4 in parallel will be, I'm just doing this in rough, 4 and 4 in parallel will be 2. So 2 and 2 in series will be 4. So 4 would be your answer of the question, like pretty standard, pretty basic question. I hope I don't need to explain here much, like what is happening, right? Very simple. They are asking you simply the time constant after t equal to 0. All you need to do is calculate the R equivalent, and 4 is not your answer actually. So you have got the R equivalent, you will have to write the L equivalent. L equivalent is 3, and you'll have to compute the time constant. So your time constant would be L equivalent upon R equivalent, that is 3 by 4, that is 0.75 seconds. So yeah, let's do this question now. If the switch S1 was closed, right, initially, and then S2 was open for a long time. Okay, S2 was open for a long time, and at t equal to 0, there is switching happening. That S1 is getting opened and S2 is closing. The value of IC of 0 plus would be, again, you're worried there are two energy storing elements, but the thing is that you know that they're asking you 0 plus, so you will not have to worry about that. Okay, so now we need to actually observe the circuit before t equal to 0 and after t equal to 0, right? So before t equal to 0, S1 was closed, right? So S1 is closed and S2 is open. So S2 is open and S1 is closed. So if I observe that your inductor will behave at steady state, it will behave as short circuit, because there will be no change in the voltage, and your capacitor will behave as open circuit, right? This will be open circuit. So what is happening? So this whole 1 ampere of current will be divided across this 100 ohm and 25 ohms. So this 100 and 25 ohms are in parallel. I can certainly find out what is the current through the inductor at t equal to 0 minus, right? This will be basically simple current division rule, 1 into 25 divided by 125, that is 1 by 5, that is 0.2 amperes, right? So through here 0.2 amperes of current is flowing at t equal to 0 minus. So what is Vc of 0 minus? It will be the drop across this 100 ohm resistor, that is 100 into 0.2, that is 20 volt, right? 20 volt. So it is 20 volts. We got the values. Now, yeah, now we know all these conditions. Now let us draw the circuit for t greater than 0, right? For t greater than 0, S1 will be opened certainly, and S2 will be closed. So S2 will be closed, and we know this will carry a current, like this will try to keep the same current, that is 0.2 ampere, and this will try to maintain the same voltage, that is 20 volt, right? So this half is gone. Okay, we don't care about this half. You will say, sir, how this current is becoming 0? So there must be some other circuitry here, right, that will connect this current source. Don't worry about that. Okay, now here we have 0.2 amperes of current, and this voltage is 20 volts. So this voltage is 20 volts, so I know the current across this, right? That will be 20 upon 25, that is actually 0.8 amperes of current, right? So this is 0.2, 0.8. So through the capacitor, from the positive terminal, what will happen? From the positive terminal, your 1 ampere of current will leave. Okay, so this is the direction of the current that I am telling. This is the actual direction of the current, 1 ampere, but their reference direction is downward. Their reference direction is downward, right? Okay, is there any impulse current that is flowing through the capacitor? No. So there will not be any sudden change of voltage, so we are safe. Is there any impulse voltage that is getting applied across the inductor? No. This voltage is finite, this voltage is finite, no impulse voltage, so we are safe. So basically your capacitor current at 0 plus would be simply minus 1. 1 ampere, because we are applying KCL here, 1 ampere, and minus because it is flowing in the opposite direction, not in the same direction, right? That's why it is negative. So option B would be correct. Option B would be the correct answer for this question. Okay, let's move on to the next question. So this is the next question, and with that we will be done with the easy questions, and then we will obviously solve the double questions are pretty good, right? In the circuit shown below, the switch S was closed for a long time. The switch S was closed for a long time, and it is open at t equal to 0. The maximum magnitude of the voltage VR in volts would be equals to what? So if it was closed for a long time, right? It was closed for a long time. So if it was closed for a long time, what was the current at across the inductor at t equal to 0 minus? Because the inductor current does not want to change, right? Certainly. So current at t equal to 0 minus, this will behave as short circuit because it will reach steady state. If it reaches steady state, simply this circuit will be 2 by 1, right? That is 2 ampere, because this will be short circuited, no current will flow through this 2 ohms. So all of the voltage will be appearing across this 1 ohm. So it will be 2 amperes. That will be the initial current across the inductor at equal to 0 minus. So yeah, now if I solve this, how do I solve this? So let's now draw the circuit at t equal to 0 plus, right? At t equal to 0 plus, switch will be opened, right? Switch will be opened, and this inductor has some current, right, in this direction. This was the direction of the current that we assumed, right? Because this is the direction of the current previously. That is 2 ampere. It will try to maintain the same current. It will try to maintain the same current, right? Now this switch is open, so there is no current coming from here. So this is a network, right? So output current also will be 0 here, right? Because the sum of currents should be same, incoming and outgoing. So this will be 0, this will be 0. So, but this inductor wants to keep the current as 2 ampere. So it will develop a voltage such that some current will flow through this resistor in parallel. So this 2 amperes of current will flow through this resistor. It will not change. It will not change the current. Like the inductor current will not change suddenly. So the drop across the resistor will be plus minus 4 volts like this, because the current will flow in the same direction, right? Current will not change suddenly. Current will still flow in the same direction. So it will be plus minus. Resistor, we know current only enters the positive terminal. So this will be plus, this will be minus. So actually the voltage VR, maximum magnitude of the voltage VR would be 4 only. Okay. It will be 4. Although they have given the VR in opposite direction, opposite sign, but they are asking me the magnitude, right? It will be 4. Why it will be 4? Sir, why not more than this? After t equal to 0 plus, it can go more than this, right? No. Because what will happen, the inductor, right, will only de-energize. Because what is happening? Current, if you see, this is plus minus, right? So current is leaving the positive terminal. So the inductor is delivering power. If the inductor is delivering power, energy is reducing across the inductor. So you half Li square, right? This is reducing. So half and L are constant. So I has to reduce. If I reduces, this I into 2, right? That drop across the resistor will reduce. So this I is always reducing. The voltage after this will only reduce. It will not increase, because this is a source free network. So voltage only will reduce. It will not increase. So as this is a source free network, voltage will reduce. So we are safe. So they are asking me the magnitude. So they have played it very safe. They are asking me the magnitude. Sign I know, but as they are asking me the magnitude, the maximum voltage magnitude would be 4 volt. This will be the answer of this question. So yeah, let's begin with the WP questions. So W has like all the most of the questions were good actually, right? So I think a good revision has happened for you guys. A resistor and a capacitor are connected in series to a 10 volt DC supply. So resistor and a capacitor is connected in series to a 10 volt DC supply. Great to know. And a switch is also there, right? Through a switch. So the switch is also there. So let me draw the switch. The switch is closed at t equals to 0. The switch is closed at t equal to 0. The capacitor voltage is found to cross 0 volt at t equal to 0.4 tau, right? Where tau must be the time constant, circuit time constant. Okay, so it is crossing 0 volt at t equals to 0.4 tau. So that basically means that they are suggesting me that the initial voltage across the capacitor must not be 0. It must be something non-zero, something negative, right? Because if it is negative, let's say -4, then only we know at steady state what will happen. Steady state, the capacitor will behave as open circuit. There will be no current across the resistor. So all of this voltage drop will be across C. So at steady state, Vc of infinity will be 10. So if I am crossing my 0 volt after t equal to 0, that certainly means before t equal to 0, right? The voltage was something negative. Then only I will be able to cross from, I will be able to go from -4 to 10, and I will have to cross 0. Otherwise, let's say if initial voltage was 2, that basically means I will go from 2 to 10, right? And the voltage will never cross 0. That is not possible. Okay, now they are asking me the absolute value of the percentage change required in the initial capacitor voltage if the 0 crossing has to happen at t equals to 0.2 tau. Now they are telling me if the 0 crossing will happen at t equal to 0.2 tau, then what will be the absolute value of the percentage change in the initial voltage across the capacitor? So basically they are asking me if they are asking me the absolute value of the percentage change. So percentage change generally means basically the final, like Vc2 of 0 minus magnitude, because they are talking about the absolute value. sorry, Vc2, not absolute value of the percentage change, so not magnitude here. Vc2, the second time of the initial voltage minus the first time, right? Vc1 0 minus upon Vc1 with respect to the reference, basically Vc1 into 100, and they're asking me the absolute value, so I will take the magnitude, right? That is what they're asking. The change upon the initial value into the 100 percentage, that is what they're asking me, right? So for that, first of all, I need to compute what is Vc1, and I need to compute what is Vc2. Vc2 would be the case when my zero crossing point happens at t equal to 0.2 tau, right? So let me first of all, this is a very simple first order equation, right? First order circuit. So the equation of the voltage across the capacitor Vc of t would be equals to Vc of 0, sorry, Vc of infinity, that is simply 10, right? Infinity voltage is certainly known to us, that is 10 volts, plus Vc of 0 plus. Okay, now in this case, right, we will the voltage certainly change? No, it will not certainly change. Whatever was the initial voltage, that will remain that way, because let's say if the initial voltage was -4 and I apply 10 volt, right? So what is the current? Current would be 10 minus of -4 divided by R. That is some, if R is let's say 1 ohm or 2 ohm, right? That is some finite value, not infinite. If it is not infinite, so no problems. If it is not infinite, so no problems, right? So current is finite, so capacitor voltage will not change instantaneously. So whatever was the initial value, right, Vc0 minus, that will be the same value. Vc0 plus and Vc0 minus will be same. Then minus of infinity into e raised to power minus t upon tau. Now they are telling me that my Vc of t will be 0 initially at t equals to 0.4 tau. So this value will be equals to 0, 10 plus this will be okay. So here we'll be able to comment on Vc0 minus, right? So Vc0 minus would be equals to, this will go there minus 10, okay, so minus 10 into e raised to power 0.4, and then I will add plus 10, right? So what will be the value of Vc0 minus? Hold on a second, I'm doing something wrong. This will be added, this will go point, so t upon tau, that is correct. Tau is r into c, that is a time constant, right? R into c. So this will be infinity, this will go on that side minus 10, and then I will multiply both sides by exponential. This will go on that side, then I will add plus 10. That's it. Okay. Hold on a second. 0.4 exponential into 10. Yeah, this is negative, more negative, right? That makes sense. That is what I was thinking. It cannot be less than it cannot be like more than 0, right? It has to be negative, and it is coming out to be negative. So it is right only. So 4.918. Okay. Now what they want is, this is the voltage in the case 1, that is Vc1, right? In the case 2, everything will be same. All they want is the zero crossing to happen at 0.2 tau, not 0.4 tau. So this will be 0, left hand side will be 0, this will be 10 plus Vc2 of 0 minus 10 into e raised to power minus 0.2 tau and not 0.4 tau, right? So this will be basically Vc2 of 0 minus would be basically 10 into e raised to power 0.2 plus 10, right? So 0.2 exponential into 10 plus 10, that is minus 2.21 volts. Okay, so now they're asking me the ratio. I have to compute this, right? Vc2 minus, so minus of 2.2 minus of minus 4.981. They're asking me the absolute value, so we don't have to worry about signs here. Just the difference upon the initial reference and the absolute value into 100, because they are asking me in percentage, right? So this plus 4.918 upon 4.918 into 100, they are asking me the absolute value. So it is 54.98 percentage, right? So they have asked to round up to 2 decimal places. So 54.98 will be your answer for the question. Again, like question is simple but bit unique, right? It's a simple RC circuit, nothing else. But the way they have asked the question is unique. So you have to be very active, right, during solving these kinds of questions. So let's solve this question. So in the circuit, switch S is in closed position for a very long time. So it is closed for a very long time, right? If the switch is opened at t equal to 0, then the current expression would be across the inductor. It's very simple, right? So all we have to do is find out the current before t equal to 0. So when it is closed, this whole thing will be short circuited. So this is simply 0 volts. So if I, and your inductor also will behave as short circuit at steady state, right? So if your inductor behaves as short circuit at steady state, so simply this current across the resistor would be 10 by 1, because this is also 0 volts, this is also 0 volts. So this will be 10 amperes, right? So, and this resistor is in series with the inductor, so the current across the inductor will be 10 amperes. So that is done. Current across the inductor is 10 amperes, that is fixed. Now if the current across the inductor is 10 amperes, right? Now how do I comprehend? So this is a first order circuit, right? So what will happen at t equals to infinity? At t equals to infinity, again the inductor will behave as short circuit only, right? But what is happening at t equal to 0 plus? At t equal to 0 plus, suddenly the switch will be opened. As soon as the switch will be opened, these two sources will be in series. This whole branch will go away, right? And the current through the inductor we calculated, it was 10 amperes, right? Before closing the switch, sorry, before opening the switch. Is any source limiting here to pull 10 amperes? No. So this voltage source will not be very angry if I say that the inductor wants 10 amperes, and this voltage source also will not be very angry, right? They will allow the 10 amperes to flow. So there is no problems here. So there is no impulse voltage. So we are safe. And anyways, we can see these voltages are finite, not infinity. So no impulse voltages. So we are safe there, right? And at infinity, what will happen? Basically, your inductor will again behave as short circuit. If it behaves as short circuit, so again, so your IL of infinity current, right, would be equals to, what is the overall voltage now? Overall voltage is now 40. Overall voltage is now 40. Right? If you see, if you apply the KVL here, you will find out the current. It will be 40 upon 5, right? 40 upon 5 ampere. 40 upon 5 ampere, which is 8 ampere. So at t equals to infinity, the current across the inductor will be 8. So if I see in this equation, current across the inductor becomes 0, not possible. In this equation, it is 10 at t equal to infinity. In this equation, it is 10 at t equals to infinity, not possible. Only this option is possible. At t equals to infinity, current is 8 ampere, and if I put at t equal to 0, right, this will be 8 plus 2, that is 10 amperes. That is correct. Now, one small thing, if let's say this resistance value, right, was 3 ohms. If this resistance value was 3 ohms, then what would have been the current at infinity? It would have been 40 upon 4, right? Because 3 plus 1 is 4, that is 10 ampere. So 40 upon 4, that is 10 ampere. So yeah, we got this value of the current across the inductor. So what will happen? What will happen? Your inductor initial current was what? 10 ampere, and final current is also 10 ampere. So it is already in steady state. Inductor will say the circuit wants me finally to go to 10 amperes, and initially also I am at 10 amperes only. So actually there will be no change in the current. The current will always remain at 10 amperes only across the inductor. That is the beauty. I'm just telling you the answer is this, option C. I'm just telling you a different question. What if the resistance value was 3 ohms? That is what I'm telling you. So in that case, the current will be always 10 ampere. In that case, your option B would have been correct. Okay, that is the beauty of this question. So there will not be any transient, because inductor does not even need to change its state, because the circuit is telling me finally you need to go to 10 amperes. An inductor already has 10 amperes. So inductor will happily say, I'm already at 10 amperes. Why will I change my state? I will remain at 10 amperes. So it will always be at 10 amperes. So if this resistance value was 3 ohms, right, then the question option would have been, correct option would have been option B. Okay, let's solve this question. Now this question is very good actually. Honestly, I will say this question is pretty good. Now from the starting itself, I want to say, if you want to comprehensively understand pulse response, go and watch this video. Starting only I will say, because I will say a lot of things here that might go over your head, right? So I want to give you a warning. Don't just blindly think that whatever I will say you will be able to understand. I will say a few high level stuff that if you have already studied pulse response previously, you will be able to pick up. Okay, so if you have not, and if you understand whatever I say, everything I say, you will have to go and watch this video. Okay, so yeah, let's come back. Okay, so a 100 hertz square wave is given. Generally, square wave has a 0 DC value, but here they're directly mentioning the lower limit and upper limit. It varies from 0 volt to 5 volt, and if they're not mentioning what is the on period, off period, right? What is the period for 0 volt and 5 volt? You will assume 50%. You will assume 50% duty cycle. So the on period would be on period would be, right, this is my input Vi, %50 on, 50% time off. Okay, and switching frequency is capital T. This is T by 2. This is 5 volt, and your capital T would be inverse of the frequency, that is 100, right? 1 by 100. So that is the time period basically. Okay, so we got these values. Now the output voltage waveform across the resistor is 6.2 volt peak to peak, right? So output voltage across the resistor that they're telling me is 6.2 volt peak to peak. So delta VR, right, or the delta VO is equal to 6.2 volt peak to peak, and the resistor value R is equals to 820 ohms. Then they're asking me what is the capacitance value. Pretty interesting question, right? So if your input is a periodic voltage, right, your output also will be somewhat a periodic voltage only. Your output also will be a periodic voltage only. Input is periodic, output also will be periodic, because it is a linear kind of system that will happen. Now there are two cases. Okay, there are two cases. I will tell you a lot of things here, right? I hope you can pick it up. If you don't, again go back and watch this video. I will tell you different kind of analysis. First approach would be the time domain approach. Time domain approach. Okay, time domain approach, there can be two cases. One, my time period is very greater than the time constant of the circuit. In this case, the time constant is R into C. So time period is very greater than time constant of the circuit, and basically time period is much greater than 4 into tau. And in the transient equation, I forgot to tell you that at 4 tau, the value of the current or voltage, right, almost reaches steady state. It is almost 99% of the steady state value at 4 tau. At 4 tau, the value of the current is almost 99% of the 99% of the full value. Sorry, of the steady state value, right? At 4 tau, 4 times the tau. This I know you have studied, so I'm just saying it again. So if time period is much greater than 4 tau, right? So basically I'm applying the voltage, this input. So basically I can say that the T by 2 for which the input voltage is applied, right, 5 volt is applied, is much greater than 4 tau. So if T by 2 is much greater than 4 tau, what does it mean? basically means that I am applying this 5 volts source always, right? So basically I'm giving the circuit enough time to reach steady state. I'm giving the circuit enough time to reach steady state. I will go a bit fast here. So if I'm giving enough time for the circuit to reach steady state, so what will be the steady state value of the voltage across the capacitor? The voltage across the capacitor will be 5 volts steady state, right? And then again, after T by 2, the current will go to 0. If the current goes to 0, then I'm giving enough time for the circuit to discharge, right? Because if the voltage goes 0, this will be short circuited. If this is short circuited, the capacitor has still voltage of 5 volts, so it will totally discharge. So the voltage uh, will reduce, right? Voltage will slowly reduce, and voltage reduce, and it will go to 0 at steady state. Again, it will remain at 0 till the next pulse will come. So again it will go like this, and again it will go down, right? That is the scenario when my T by 2 is very greater than 4 tau. Okay, so now this is the capacitor voltage, but they are talking about the output voltage. Can you tell me what will be the output voltage? Your output voltage is very simple. What is the current? So capacitor current is nothing but the, so I can first of all compute the current. So capacitor, like current would be same as the resistive current will be same as the capacitor current, and the capacitor current is nothing but the derivative of this, right? IC is equals to C dVc by dt. So if I differentiate this, the graph will be somewhat like this. Initially suddenly the current will increase. Why it will increase? Because initially let's say capacitor had 0 voltage, right? Previously if you see, capacitor here had 0 voltage, and suddenly I'm applying a voltage of 5 volt. So this will be short circuited, and the current will be 5 by R. That will be the highest current, and slowly this capacitor voltage will increase, and slowly the current will reduce and go to 0. If you did not understand it, unfortunately you will have to go and watch the video. You'll have to go and watch the video, right? Now what will happen is, this is the case for yeah, so from 0 to T by 2 this will happen, right? And at T by 2 what will happen? This will go negative, right? Why negative? Because this will be shorted, right? And all this current will discharge. So the current, previously the current was flowing like this, now the current is flowing in this direction. It is leaving the capacitor, right? Positive terminal. Previously it was entering. That's why the current will become negative. Hence the voltage also will become negative, because simply your voltage is nothing but the current times the resistance, which is a constant number. So this will be the output voltage graph. Now this was the case when my T is very greater than 4 tau. When my T is very less than 4 tau. When my T is very less than 4 tau. So T is very less than tau actually. So basically your T by 2 also will be very less than 4 tau, right? This condition will be still valid. If T by 2 is very less than 4 tau, I will just say in a quick manner, what will happen is the output will oscillate between the, so not the output, the capacitor voltage will oscillate between the average value of the input. In this case, the average value of the input, I hope you know how to compute the average value of this waveform, that is 2.5 volts. So that would be 2.5 volts over here, right? Now you will say, sir, why average value? I will just give you a bit of intuition. Remaining things you will have to do on your own. So what happens actually, right? This voltage, if I do the Fourier series expansion, it will contain all components. It will contain DC component because it has a DC value. It will contain F component, right? Then 3F, then 5F. Why? Because this waveform is half wave symmetric, and this waveform, if you do some symmetry, you will find out this waveform is half wave symmetric. So that's why the even harmonics will be absent, only odd harmonics will be present. What happens is this capacitor, right? If we have, so I'm only discussing about the capacitor right now. So I'll just give you a bit of intuition here. I'm talking about the capacitor voltage right now, ignoring the resistor right now. So this is a low pass filter, right? You can draw the transfer function. This will be a low pass filter. Okay. And for a low pass filter, like in this condition, right, your t is much less than tau. If I take the inverse, this will be 1 by tau is much less than 1 by t. So 1 by tau is nothing but 1 by RC, right? And this is 1 by t is f. So your frequency of the input, right, is much less than the cutoff frequency. This is the cutoff frequency of the low pass filter. Okay, I'm just giving you an intuition. If you want to understand more, go and watch the video. So the low pass filter graph is somewhat like this, right? So the frequency, right, f is much greater than the cutoff frequency. So all these components will be rejected. Only this component will be accepted. Why? Because it is behaving like a low pass filter. Now I know this is a high pass filter. This is a high pass filter. But because I'm only discussing about the voltage across the capacitor, that's why I just converted the circuit for easier understanding. So only DC component will be passed because low pass filter does pass DC component. So whatever is a DC component, that will be passed. And yes, now you might say, sir, if only the DC component is passed, only 2.5 volts should always stay there. Yes, you are correct. But what happens? This is not an ideal low pass filter. Still there will be some gain. If there is some gain, these components will be passed but with high attenuation, right? Let's say the multiplication factor will be 0.1, 0.01, 0.5, 0.005, something like this, right? There will be attenuation. So that's why this ripples are there due to the high frequency components. Okay, that was the summary. Okay, but in this question, right, nothing is mentioned to you. Like you cannot actually compare your frequency with the time constant. You cannot compare it. If you cannot compare it, then this, right, this particular equation, this particular thing that you see linear, this is a approximated curve. The actual curve is something like this, actual curve. So whenever no relation is given, right, then you will actually plot the actual curve. What is the actual curve? So this word, this is simply a first order circuit, right? So transient equation will always be valid. When the 5 volt source will be connected, you can use the transient equation. When the 0 volt source will be connected, you can use the transient equation, right? I don't see any harm in using the transient equation. You are correct that it will not be able to reach the steady state because there will be switching of the voltages. It will not be able to reach the steady state, but you can still apply the transient equation. So this is an approximated equation. Actual equation is something like this. When the 5 volt source will be connected, the voltage will increase exponentially across the capacitor, and then when the 5 volt source will be taken out, right, the voltage will reduce exponentially, and this will keep on happening, right? Because I have made this approximation, we can do this, and more about this you will learn in this video. Okay, so that's why we can do this. So this will toggle between VO max and VO min, VC min and VC max. Your waveform will be certainly periodic. No one can deny that because your input is periodic, your waveform also will be periodic only, right? Okay, so it will be VC max, but this is the capacitor voltage, but they're not talking about the capacitor voltage, they're talking about the output voltage. So when the source is connected, the capacitor voltage will certainly increase because it will energize. So when the source is connected, right, what is the output voltage? VO is equals to VS minus VC, right? If you see, this is my output plus minus VO. This is my input. So this is my VC and this is my VS. So VO is always VS minus VC, right? So VS from 0 to T by 2, it is 5 volts. So your VO would be 5 minus VC, right? So this point, right, okay, 5 minus VC. So it can be negative as well, and it will be negative actually. So it will not be negative, it will be positive, certainly. It will be something positive because initially the capacitor is energizing, so current will be flowing into the capacitor. So initially when I apply the voltage, right, 5 volt, what is happening? Current will flow in this direction, that will increase the capacitor voltage. So if the current flows in this direction, so plus minus VO will be this. So polarity will be like this. So we'll start from plus, right? We'll start from plus, and then what will happen? then at t equals to t by 2, the current will reduce because the capacitor is trying to reach steady state. So it is 5 minus Vc. So this will be Vc max. So 5 minus Vc max, maximum value. So voltage will be lower. At t equal to t by 2, suddenly there is switching. When there is switching, if I draw the circuit, so the capacitor voltage is now Vc max, and previously the current was flowing in this direction, right? Because the source was there that was energizing the capacitor. But now there is no source, and capacitor will try to maintain its voltage. So current will now flow in this direction. So basically the capacitor will discharge, right? So now the polarity has flipped. Although this value, right, is same. This value is same. Let's say this is some VO min, right? But this will suddenly go negative. Okay, and this cycle will keep on repeating. This was a very good question actually, right? So this will be VO min, right? VO min, and this will be VO max, because suddenly the voltage will be applied, right? If the voltage is applied, the VO max will be there. Okay, so what are they telling me? That they're telling me the ripple in the output voltage, the peak to peak ripple, in the output voltage is 6.2 volts. Okay, peak to peak ripple is 6.2 volts. What does it mean? They're talking about what output voltage. So this will be Vc VO min. Go down to this value. Hold on a second now. Hold on a second. This is okay. Let me just think about it. So this will be 5 minus Vc max, right? That is your VO max. 5 minus Vc max, right? Vc max, and sorry, 5 minus Vc min, right? Sorry. At t equal to 0, the voltage will be 5 minus Vc min, not max, because the voltage across the output would be maximum. Now at t equals to capital T by 2, what is happening? The voltage is, capacitor voltage is Vc max. So this VO min would be 5 minus V Vc min actually. Okay. Okay. Now if suddenly the output is removed, right? Okay, this is not VO min actually. Sorry, this is not VO min. That is my mistake. This is not VO min, right? Suddenly, if the output is removed, right, what will happen? This voltage will become, okay, sorry. Whatever. This is Vc max, right? 5 minus Vc max. The minimum voltage will be 5 minus Vc max. Now, suddenly, if the 5 volt is gone, so the voltage across the load, right, output would be minus Vc max. So they are talking about this ripple, right? Peak to peak, this ripple. Okay, and this will be periodic. Don't worry, this will be periodic. They're talking about this ripple. So what is the ripple here? Delta V out. Delta V out would be the maximum value minus the minimum value, right? So 5 minus Vc min minus of minus Vc max. This question is actually pretty good, and most of the institutes will totally ignore this question, right? They will not solve this question. They will not explain you properly. Okay. So now what is happening? This will be delta VO is given, the ripple is given, that is 6.2 volts. Ripple is 6.2 volt peak to peak, right? That is given to us, 6.2 volts. And this value is basically 5 plus Vc max minus Vc min. Okay. So your Vc max minus Vc min comes out to be 1.2 volt. So the peak to peak ripple, right, across the capacitor will be 1.2 volt. They're actually asking me the capacitance value. That certainly I will solve. I will certainly solve that. How? We can use the transient equation when the input source is applied. 5 volt. When the input source is 5 volt actually. Here we have this capacitor that had an initial voltage of Vc min, right? It was the lowest. Then it started charging and the voltage would increase. And here I have the resistor. So from t equals to, let's assume from t equal to 0 to t equal to t by 2, the voltage will go from across the capacitor, the voltage will go from Vc min to Vc max, right? That will happen. If you see the graph from t equal to 0 to t equal to t by 2, the voltage goes from Vc min to Vc max. So we can use the transient equation, right? Let me first of all write the expression of capacitor voltage in this case. What is the value of the capacitor voltage Vc of t, right? In this particular condition, circuit condition, it is final value. What is the steady state value? It is 5, right? 5 volt. Steady state value would be 5 volt across the capacitor plus initial value. Initial value is what? Vc min. Initial value is Vc min, right? And minus the final value, that is 5. That is e raised to power minus t upon tau. Okay. Now we know at t equals to capital T by 2, the value of the capacitor voltage is actually Vc max, right? So at t equals to capital T by 2, the value of the capacitor voltage is Vc max. Okay. So this value is Vc max, right? So Vc max is equals to 5 plus Vc min minus 5 into e raised to power minus capital T by 2 upon tau, basically 2 upon t upon 2 tau, right? Okay. So now how do I solve it? This should be equals to Vc max, right? This is one equation. Okay. This is the analysis of the circuit from t equal to 0 to t equal to t by 2. Now again, let me analyze the circuit from t equal to t by 2 to t equal to capital T. So during capital T, the circuit will discharge, right? So analyzing the circuit from t equals to, so we will start off, now we will start off from Vc max because the supply has gone and just my capacitor voltage has reached the maximum value, right? So we'll start from Vc max and this will be C, this will be R, and this, your supply source is gone, it is 0 volts, right? So this will be 0 volts. So now it will discharge, right? So what will be the equation in this case? In this case, again the capacitor, this is from t equal to capital T by 2 to capital T. So Vc of t would be, what is the initial value now? So what is the final value? Final value is 0, right? It will reach steady state, the capacitor will be open circuit, no current, so voltage will also be 0 because the current across the resistor is 0. So V equals to IR, so 0. So final value is 0 plus initial value is Vc max minus the final value 0 into e raised to power minus t upon tau. This will not change, tau will not change, it is the same circuit, time constant does not change, right? Now again I will put the same value at t equals to capital T at, okay, just give me a second, this will be t. Now here, right, actually this will be t minus capital T by 2. Why? Because the time period that I am considering, right, it starts from t by 2. Okay. So yeah, if you're confused, you will need to go and watch the transient video, because here what is happening? The switch actually is closed at t by 2, not at t. The switch is closed at t by 2, not at t, right? Like I'm just simulating this circuit with the help of transients. So switch is not closed at t, right? Because currently the time is going from capital T by 2 to, so now this will be capital T by 2. Capital T by 2 to capital T, right? So this will be t minus capital T by 2, not t. I hope you get the point why this will not be only small t, because the voltage across the capacitor is Vc max at what time? At t equals to capital T by 2, not at t equals to 0. So initial voltage is Vc max at t equals to capital T by 2, not at t equal to 0. At t equal to 0, the voltage is Vc min, right? So if you put here, if you don't write t minus capital T by 2, if you write just t, so if you put here t equal to 0, sorry, if you put here t equal to capital T by 2, your Vc of t will be something else. It will not be Vc max, but it is supposed to be Vc max at t equals to capital T by 2. So we certainly have to put here t minus capital T by 2. Otherwise, your equation will not be satisfied. If you now put t equals to capital T by 2, you will see your Vc of t is equals to Vc max. There are more things, and if you want a bigger explanation, go and watch the video, pulse response. Okay, so yeah, now we can totally consider, now at t equals to capital T, what is happening? T equals to capital T, the voltage would be actually Vc min, right? T equals to capital T, the voltage is Vc min. So this will be Vc min equals to Vc max minus, so this is 0 only, e raised to power minus, sorry, this will be by tau. So capital T, this will be t by 2 tau. So from this, what do I want? I want the value of tau actually, because I need to find out the value of C. So and your C is like tau is equals to R into C. So I need the value of C, that is tau by R. So if I get the value of tau, I know the value of R, I will be able to calculate the value of C. So this is one equation and this is other equation, right? So do I have any other alternatives here? So I know this value, right? Okay. So there is no other alternative. Let us take the ratio of these two. If I take the ratio of these two, what will happen? This will be Vc max. And don't, trust me, don't try to solve this question in the exam hall. This will be a very lengthy question, right? These questions are there just to scare you. Like this looks cool because I'm solving it and there are a lot of concepts. I do agree. But honestly, I will say, I will solve this question at the end because this is very lengthy. There are a lot of things here, right? I will not solve this at the starting. I will try to solve and I will see that this question is going very lengthy. So I will skip it for now and I will solve other questions, right? So Vc max, so it looks cool, like we also make it sound cool, but actually for your best performance in the exam hall, ignore this question, solve the easy questions, then you come back to this at the end, right? So this will come with experience, you will realize it. So Vc min equals to, okay, I cannot, okay, so let me take this 5 on the other side. This will be Vc max minus 5 and then I can take the ratio, right? And this will be Vc min minus 5 and this will be Vc max. So simply what will happen is, okay, I'm just thinking, is there an easier way out? Like, is there an easier way out? Okay. Okay, there is actually easy way out. Let's not do this. So we know your Vc max, right, is equals to Vc min into e raised to power minus t upon 2 tau. So let me okay, my screen is not moving. Let me replace my Vc max with this value. So if I replace with this value here, it will be Vc min into e raised to power minus t upon capital T upon tau equals to 5 plus this value, right? So this will be right. Let me write this as x only, right? Let me write this as x. That will be easier for me to track. Okay, so let me take it on the other side. Okay, this will anyways get cancelled, right? Okay, that is interesting. That will be cancelled. So this will be equals to 0, right? So what is happening is if I take this inside, right, VC min into this and VC min into this will be cancelled. So 5 will be equals to 5 minus 5 into e raised to power minus capital T by 2 tau is equals to 0. So your e raised to power minus capital T by 2 tau is actually equals to 1, right? And your capital T is 1 by 100, that is a frequency. So your tau, right, we can solve for tau. So just let me solve this. So 1 ln, okay, this is interesting, hold on a second. Okay, this will be capital T by 2 tau, this will be capital T by 2 tau. I'm making any mistake here. Plus VC min. Okay. One small mistake, right? This will be plus. This is not a small mistake. This is a big mistake. I'm sorry. This is a big mistake, right? This will be plus. Okay. Yeah. Sorry about that. So now I cannot. Yeah, I cannot do this. So let me write this as x and y. So let me write this. Okay. Let me keep it as it is. This will be a bit tedious for me, but that's fine. Okay. 5 minus this, right? So let me mark this value, right? Let me mark your VC minus x and let me mark this as y, right? So this is e raised to power plus t upon 2 tau is y. So this will be x into y. This will be x. This will be 1 by y, right? So let me rewrite the equation. That will be easier for us. So this will be x into y equals to 5 plus x minus 5 by y, right? So okay. Yeah. So what about this equation? Would we have we added this equation as well, right? VC max minus VC min equals to minus 1.2. So here also I can replace my VC max with x into y, right? And VC min is simply x only, that is equals to 1.2, right? So okay, that is cool. Just give me a second. Music automatically turned on. Okay, how do I solve this? This will be a bit tedious. Just thinking something, is there an easy way out here? There seems not to be. So okay, so this is x, right? We see, so your x into y is actually equals to x plus 1.2, right? So I can replace here. So this will be x plus 1.2 is equals to 5 plus x minus 5 by y. Now I can multiply by y on both sides. So this will be x into y plus 1.2 y. This 1.2 can be taken on the other side. That will be 3.8 y plus x minus 5. Okay, and we know x into y is x plus 1.2. So this will be x plus 1.2 equals to 3.8 y plus x minus 5. So x and x will be cancelled. So this will be 6.2 upon 3.8. That is what your y is. Y is basically nothing but e raised to power minus t upon capital 2 tau. Okay, so this is equals to e raised to power minus t upon 2 tau. Okay, somewhere I'm making a mistake. Sorry, this is e raised to power plus t upon 2 power, right? Y was e raised to power plus t upon 2 power. This was my y. Okay, we're not making any mistake, we're safe. Okay, so if you figure out any easier way to solve this question, please let me know, right? At least I am not able to figure out anything. Okay, so 6.2 upon 3.8 ln into 2 into 100. Sorry, this will tau will go that side. This will be into 2. Okay, this will be inverse. And so basically in milliseconds, your tau in milliseconds, right, will be tau in milliseconds will be 1021 milliseconds. Okay, sorry for the noise. 1021 milliseconds, right? 21 milliseconds. Okay, in milliseconds. Now you can solve the equation. Now we know the R, we know the resistance value. R is 820, right? So your time constant is R into C, and they have asked the C in microfarad. Okay, so they have asked this value of C in microfarad. That's interesting. So this is actually tau is 1.021 into 10 raised to the power minus 3 milliseconds. That is equals to R into C. That is 820 into C, right? So your C would be equals to 1.021 by 820 into 10 raised to the power minus 3, or I can write 1.021 divided by 0.82 into 10 raised to the power minus 6, right? We can convert this. So what will be your capacitance value? That would come out to be, just give me 1 second, right? Okay, 820. I hope I'm not making any mistake over here. Let me just quickly check once. 6.2 divided by 3.8 ln, and so your capital T is what? 1 by 100, right? Capital T is 1 by 100, and your tau would be ln of this T by 2 upon ln of this, that is 0.489, right? So this into 2 upon divided by 100. Okay, sorry, this is actually, if I multiply, so multiply this by 1000, so it is actually not 1000 milliseconds, it is 10.21 milliseconds, 214 milliseconds, right, into 10 raised to the power minus 3. So be very careful with the calculations. So extra point will come, 10.214. so this value, right, in microfarad, this will be divided by 820 into 1000. In microfarad I'm computing, so in microfarad this will be 12.45 microfarad. Now this is a very good question, like very good in the sense bit lengthy in the calculation as well, right? So your answer is 12.45 microfarad, but if you guys know any easier like solving of the equations, right, in easier method to solve the equations, please let me know. But I know in the actual exam hall few people will be very smart, sir, you could have solved it like this, you could have solved it like this, but in the actual exam hall, nothing clicks, right? Nothing clicks. Sorry for the noise, just give me 1 second, there's a flight. Yeah, in the actual exam hall nothing clicks, right? That's the problem. So if nothing clicks, you're done. So that's why I'm solving the basics. This is a lengthy question, so don't solve this at the starting, solve this at the end. Solve this question at the end. Let's solve this question. In the circuit shown below, the switch S is closed at t equal to 0. The magnitude of the steady state voltage in volts is, so the circuit is closed at t equal to 0, right? So steady state voltage will be steady state. This is a simple first order circuit, so capacitor will be open, and these two can be simplified as a single combination as 2 ohms. Here I have 10 volt and switch is closed at steady state, capacitor will be open, this will be 2, so no current will be flowing through here, so all of the current will be flowing through the 2 ohm resistor. So both of these are in series, so they're asking me the steady state voltage in volts across the 6 ohm resistor. Okay, so these two combination, right, the voltage across these two will be same if I combine these two in parallel. That should not change, right? So what is the voltage across this? Simple voltage division, right? So 10 into 2 divided by 2 plus 2, that is by 2, that is 5 volt. So the voltage across the capacitor across the 6 ohm resistor at steady state will be 5 volt. Pretty simple, straightforward, not spending too much time over here. So Yeah, let's solve the next question, this one, right? So this is the next question. So here again a lot of parameters are given to you. For time t less than 0, the steady state condition, so the circuit is at steady state with the switch k in closed condition, right? So switch k is in closed condition. If the switch is opened at t equal to 0, if the switch is opened at t equal to 0, the value of the voltage across the inductor would be, right? Again they are asking me what is the value of the voltage across the inductor at t equal to 0 if it is opened. So when it is closed, right? Yeah, sorry for the noise, really sorry for the noise. So when it is closed, what happens? When it is closed, just give me a second, right? I just want to keep a track of how much does this noise interfere with the actual audio. So so switch is closed, the inductor will behave as short circuit, the capacitor will behave as open circuit. So the circuit will be behaving like this. This will be short circuit and this will be open circuit, right? So what will happen now? This is R1, R3. So there will be current division, right? This is open circuit. There will be current division basically. So if there is current division, the current across the inductor IL is 0 minus would be simple current division 10 into the opposite resistance upon the sum of the resistance R1 plus R3. So R3 is 3, R1 plus R3, that is 2 plus 3, that is 5. So this is 2, that is 6 amperes, right? So ILO 0 minus is 6 amperes. So yeah, so this is 6 amperes. What about the voltage? So voltage can be determined by this. So what is the current that is flowing through this resistor R1? That is 6 amperes, right? And R1 value is 2. So the voltage across this resistor is 12 volts, right? And the voltage across the inductor is 0. It is short circuited. So and this has 0 current. So this has also 0 voltage. So the voltage across the capacitor at t equal to 0 minus is actually 12 volts, right? Whatever is the voltage across the resistor R1. Now something will happen. As soon as the switch will be opened, right? Multiple things will happen. As soon as the switch will open, this will be open circuited. So all of this 10 amperes of current will flow through this side, right? Now inductor will say, I will not change my current, I will keep my current same, that is 6 amperes. So the remaining 4 amperes will flow through the capacitor, and capacitor will allow the sudden change in current, because capacitor allows sudden change in current. Capacitor does not allow sudden change in voltage. So the voltage will still be like this, right? Previously the polarity, if you remember, this was the polarity, current was incoming 6 amperes, right? So this was the polarity, plus minus 12. So plus minus, this is the polarity of the capacitor voltage, that is plus minus 12 volt. Now this will remain same, and we know the current across this resistor, that is 4, and R2 value is 2 ohms. So the drop across this resistor would be how much? The drop across this resistor would be 2 into 4, that is 8 volt, right? And these two branches are in parallel. So what is the drop across the resistor R1? It is same, right? It is 6 into the R1 value, that is 2. So it is 12 volts. It is the same. So whatever was the drop across this resistance R2, this will be reflected in inductor, because they are in parallel, right? You can apply the KVL. So your VL of 0 plus will be 8 volt, and it can change suddenly, because inductor allows sudden change in voltage but does not allow sudden change in current, right? And here the voltage is also finite, so we are safe, we don't have anything to worry about. If the voltage would have been impulsive, then we would have to worry about something, that your current would have suddenly changed, right? But as the voltage is finite, current will remain same, so everything is proper. So your answer of this question would be 8 volt. Let's solve the next question. Now here the circuit shown in the figure with switch S open is in steady state, right? So S is open in steady state. After the switch is closed, the time constant of the circuit in milliseconds is, like, if the switch is closed, then I don't need to worry about t less than 0, because I need to calculate time constant. So I will just worry about t greater than 0. So if I observe this circuit, right, this is the inductor, this is the inductor, this is the inductor, this is the inductor, and there is a current source, right? Now we know for calculating L equivalent and R equivalent, we will nullify the independent sources. For current source, I will be 0, so it will be open circuit. For voltage source, V will be 0, so it will be short circuit. Okay, so it is gone, right? Now I can simplify these things, right? These inductors are in parallel, so this will be actually 0.5 Henry, right? And this is 1 Henry. Again, they are in series. This 0.5 Henry, 1 Henry are in series, and here no current is flowing, right? So this whole combination is in series with this one, that is 1 Henry. So this will be 2.5 Henry, this whole combination. So everything is converted now. This whole inductor is converted to 2.5 Henry, right? That is the L equivalent. Now what is the R equivalent? R equivalent would be the equivalent resistance across the inductor terminals, equivalent inductor. So that will be this, right? So simply these two resistors are in series, that is one of are in series. So your R equivalent is 2 and your L equivalent is 2.5. So your time constant would be L by R, that is 2.5 by 2, that is 1.25. So time constant is 1.25 seconds, that is option A. So option A would be the answer of this question, right? And this is the last question. I think no, one more question we have, and this question was pretty good, and most of the institutes, right, they did not solve it properly there, right? Although here I will not solve it totally. Again, I will redirect you to that pulse response video. You can go and watch that pulse response video. I will just say you intuitively how can you solve this. Already I have covered a lot in the previous question, that pulse question, right? So in the circuit shown below, if the values of R and C are very large, so R and C values are very large. So if R and C value are very large, that means your time constant tau is equals to R into C is very large. So they are giving me a hint that your tau is very large, right? Okay, tau is very high. Now they are telling me the form of the output voltage for a very high frequency square input whose ripple is from +1 to -1. So its DC value, DC is 0, right? So it is high frequency. Frequency is very high. That means your time period is very low. Now what is the comparison? Your time constant is very high. Your time period is very low. So what will happen? Simply your T will be very, very less than tau. I have covered this in the previous question. So please go back to the previous question of the pulse response, right? That question, this question, this one. We covered a lot of things here in this question, right? Question number 13. So please go back and watch this. Yeah. So in this case, right, what will happen? So basically, again, if I analyze this in the frequency response, right? So what is the cutoff frequency? That is 1 by tau. That is the cutoff frequency. So your cutoff frequency is much, much less than the input frequency, right? Fi. And this is a RC low pass filter, right? So RC low pass filter, the behavior is like this, and it does not have a DC component. So output voltage will be what? It will be almost 0 because your input frequency is very high and none of the components will be passed, but there will be a bit of ripples as has been explained in the previous question, right? There will be a bit of ripples as has been explained in the previous question. Now I see this one is varying from -1 to 1. Will it vary linearly from -1 to 1? That it will not happen. It will certainly, it will vary from some minimum value to maximum value, but it will not vary from -1 to 1. Why? Because if you are saying that it is varying from -1 to 1, right? Let's say at certain point it is -1, right? -1. What will happen? That if you say that this is the scenario, right? So these are anyways wrong. That is clear, right? Why these two are the only question that can come into your mind, because I've already discussed in the previous question why this will be the graph, right? Actually the graph is this, but in this case there is no DC value. So if there is no DC value, the graph has been shifted down to the center, right? That is what is happening. Now you might have a doubt. So these are gone. Option B and option D are gone. Whether this will be the answer or this will be the answer. Why this will not be the answer? This will not be the answer because if you see that you are saying that your voltage, right, is going from -1 volt to 1 volt in half the time period, right? This is half the time period. Is this even possible? So basically 1 volt is what? 1 volt is a steady state voltage, right? So let me draw the circuit when the input voltage is 1 volt. So when the input voltage is 1 volt, right, from let's say t equal to t by 2 to t equal to capital T, and this is my resistor and this is my capacitor which has some voltage. Let me assume it to be -1 voltage, no problem. Now you are saying that from capital T by 2 to capital T, the voltage basically reaches to +1 volt. It goes to +1 volt suddenly, right? I mean it is able to reach to +1 volt, but that is not even possible. Why? Because your time constant, just give me a second, your time constant is much greater than your time period. So you're not providing enough time for the circuit to totally reach the steady state because your time constant is lower, because circuit will reach steady state at 4 tau. But you're saying that at capital T by 2, in T by 2 duration only, the circuit is reaching steady state. And I know T by 2 is much less than tau according to the question. So it will certainly not reach the steady state. It will certainly not reach the steady state. That is, I'm sure about that, because the time period given is much less than the time constant. There is not enough time for the circuit to reach steady state, that is 1 volt. So certainly this will not be the answer, right? So this will be the answer. Now there are more ways to understand why this will be the answer, right? That's why I'm telling you, you can go and watch that video. Multiple ways are there, but this is one way to eliminate the options, right? So that's how you can solve this question in a faster manner. Let's solve this last question. This is the last question, right? And then we'll be done. So the switch S closes at t equal to 0 second. The time in second the capacitor takes to charge to 50 volt is what, right? So the capacitor needs to charge to 50 volts, right? Initially the switch is closed at t equal to 0. So before t equal to 0, what are the circuit condition, right? So the switch is open. So if the switch is open before t equal to 0, what happens? Capacitor will behave as open circuit if it has reached steady state. So this will be open circuit. So there will be no current flow here, and there will be no current flow here as well, right? So technically there will be no current flow here. So all of the current flow will be through here. So there is, okay, so all these 3 amperes will flow through this 25 ohms. So here also there will be no current flow, right? So basically there is no current flow from here. So the drop across this resistor is 0. So all of this voltage, right, let me assume the polarity, initial polarity to be plus minus. All of this voltage VC will be what? The supply voltage. VC of 0 minus would be 100 volt. That is the initial voltage across the capacitor. Now what happens? As soon as the switch is closed, as soon as the switch will be closed, right? What will happen? As soon as the switch will be closed, things will change. Again at steady state. So, okay, let me first see what will happen to the voltage, right? Will the voltage change instantaneously? Now, you know, the capacitor voltage does not like to change instantaneously unless and until impulse current flows. So, let's see whether impulse current will flow or not. So, the voltage at t equal to 0 is 100 volt here. So, through here, right, through this resistor, the current is 0 ampere actually. No problems. And through here, if this current is 0 amperes, right, and this current is also 0 ampere. So okay, this current is 0 ampere. Now what is happening? Now this, right, switch is closed. So the voltage is 0. So the voltage across the resistor is 0. So if the voltage is across the resistor is 0, so the current also is 0. V equals to IR. So all of this current is 0, this current is 0, this current is 0, everything is 0 other than this. So all of this 3 ampere current will flow through the switch, right? So I see the capacitor current is finite, it is not infinite. So we are safe. So capacitor voltage will not change instantaneously, it will remain same, it will be 100 volts only, right? It will be 100 volts only. So we are safe in that aspect, right? So now again I will draw the circuit at steady state. At steady state what will happen? At steady state, switch will obviously be closed, no problems. Switch will remain closed. The capacitor will behave as open circuit, right? Now if the capacitor behaves as open circuit, again all of this 3 ampere current is flowing through this, right? Now again 0 ampere of current is flowing, okay? Again 0 ampere of current is flowing, and okay, just give me 1 second. Switch closes at t equal to 0. Initial voltage across the capacitor is 100 volt because this was open. Okay, just a small mistake on my behalf, right? Like this is the last question, so I'm sorry, I have made a very small error. Your VC of 0 minus is not actually 100 volts. I'm sorry. So initially the switch is open, right? I'm sorry about that. I know you guys are screaming. So switch is open. If the switch is open, so the capacitor has reached steady state, so it will also behave as open only. So it will behave as open only, right? So all of this, so this current is 0, this current is 0. Now all of this 3 amperes of current will flow through the 25 ohms, right? Now this current is 0, right? Now apply the KVL in this loop. Actually that was my bad. So it will be minus 100 plus VC of 0 minus, and there is this drop as well, right? I skipped the drop here. So the drop is what? This is actually 75 volts, right? This is 75 volts. So plus 75, 3 amperes into the resistance plus 75 equals to 0, right? So your VC of 0 minus equals to 25 volts, okay? So that is the initial value of the voltage. Now again I'm again sorry. So again I will analyze the circuit after closing the switch at equal to 0 plus. At equal to 0 plus, just after closing the switch, what is happening? So this is closed, this is 25, right? And so this will behave as plus minus 25 only, right? This will not try to change instantaneously. And okay, so now this is short circuited, right? So all of this 3 amperes of current will flow through the switch. So this voltage is 0 now, right? So this voltage is 0. Now let me apply the KVL in this loop. So let me assume that this is plus minus, this will be also plus. So let me assume this current to be some IR current, right? So this will be plus 2 into IR, that is a drop. So if I apply KVL now, minus 100 plus 25 plus 25, so 2 into IR equals to 0. So your IR is equals to 75 divided by 2. So that is 37.5 amperes, right? Which is finite value, which is certainly a finite value. So no need to worry, your VC 0 plus will be equals to VC 0 minus. So this is 37.5. So no need to worry about this. Correct. So that is a scenario. Sorry, this will be 25 volts only, right? It will be same because current is finite. It is not infinite. It is not impulsive. So now we can actually solve it. Yeah. Now let us draw the circuit at t equals to infinity. Now if I draw the circuit at t equals to infinity, the capacitor will behave as open circuit. So if capacitor behaves as open circuit, right? So again this voltage is 0 only, right? So this current is 0. So this current is also 0. So actually the steady state value of the capacitor voltage Vc infinity, you can see, you can apply the KVL here, it will be 100 volt, right? So at what time the capacitor reaches 50 volts, right? So your Vc of t, it is a first order circuit, so it will be Vc of infinity plus Vc of 0 plus minus Vc of infinity into e raised to power minus t upon tau, and they are asking me when will it reach 50 volts. So Vc of t 50 will be at some time t minus 75 e raised to power minus t upon tau, right? What is tau? Tau is r into c, right? Okay, that is not that easy for us to calculate, so let us calculate that. So switch is closed, right? So if the switch is closed, switch is closed, so switch is closed, so let me nullify the voltage source. This will be short circuited and this will be open circuited. Current source will be open circuited, right? So across the C, right, if I see the R equivalent, so technically this is shorted, right? The resistance has of no use because I am technically shorting the resistance. So technically the R equivalent is 2 ohm only and the C equivalent is 5. So R equivalent into C equivalent, that is 2 into 5, that is 10. Okay. So your answer would be minus 50 by 75, that is 2 by 3 ln into minus of tau t. Okay. So let me write the values. This would be 2 by 3 of ln negative into tau is 10. So 4.05 seconds, right? 4.05 seconds. T equals to 4.05 seconds. This will be the answer of this question. So with that, we are done with all the questions. If you have enjoyed this lecture, please hit the like button. Please comment down below whatever portion you have enjoyed, so that other students can understand like what kind of content we are teaching here. That is something different. That is something different from all other institutes, right? So yeah, that will just help us out because we are providing so much for you guys. We are doing so much for you guys. So just a bit of things in return that we expect. So yeah, I will see you in the next video. Until then, happy learning.